Sarbash, if you can mute your microphone, otherwise we can hear the background noise. Thanks.
Hello.
So I guess.
Hello, Maria Giovanna. Can you hear me?
Hi, Massimo. Can you hear me?
Yes.
Okay, perfect. So it's 9 a.m. Italian time, so I guess it's time to start. I would like to welcome everybody to the second week of the 6th Bego Rencontre Summer School. And today we have the pleasure to hear from Professor Della Valle, who will tell us about the empirical grounds of GRB supernova connection.
Okay, thank you very much
The floor is yours.
for your nice words. And okay, here next slide show, if I okay here the summary of my my talk. I start with gamma reverse supernova properties, then I comment about the progenitors, both in terms of environment and mass, size. I will expand the issue of gamma reverse supernova rates, and finally I will present they are not really conclusion, but they are more open issues than conclusions. Okay, here we have the zoo, the supernova zoo, and we discovered that the supernovae associated with gamma reversed represent a tiny fraction of this 1 BC family, which basically are core collapse supernovae that explode when they have already lost the huge envelopes of hydrogen and helium. And this happened to stars that have a mass that on the main sequence that typically is larger than 8 solar masses. And the connection between gamma reversed and supernova were finally established in 98 when the supernova 98 BW was found to be associated with GRB 980425. And what was observed was a supernova with an incredible, a large kinetic energy of the order of 3 times 10 to the 52 erg, which correspond to about 30 times the kinetic energy that was associated with the supernova 9087A. Today we know, okay, this was a list of gamma reverse supernovae that was provided by Kovacic and collaborators in 2014. Today we are probably, I mean, I didn't make the exact computation, but we have about 60 of these systems. However, I would say that 95% of what we know about gamma reversed and about supernovae associated with gamma reversed are really on half a dozen of objects, and obviously they are the closest because they can be investigated with details with respect to far away objects. The first property is that is really, let's say, very, very clear when you look at the spectra of this supernovae is the lack of hydrogen and helium in the ejecta. And this automatically, if you remember the first slide, one of the first slides that I showed a moment ago, that correspond to this 1C supernova. Then it's very clear that if you compare a spectrum of this gamma ray burst supernova with the spectrum of normal, not normal, sorry, let's call them standard core collapse supernovae, you see immediately differences in the morphology of the bright lines that appear in the spectrum. And these and these broad features that you see in the spectrum here at your left are basically due to the large expansion velocity that characterize the ejecta of gamma-ray burst supernovae, about 30,000 kilometers per second. That is much, let's say, is at least 3 times as large as it is observed in standard core collapse objects. So as a result of this, the kinetic energy associated with the ejecta is about 10 to the 52 erg. That is an order of magnitude larger than standard core collapse supernovae. The range of luminosity is also quite large, and this implies that a relatively large amount of nickel is synthesized during the last stages of stellar evolution, and this corresponds to peak luminosity that in some cases is as faint as the faintest star core collapse supernovae, and in other cases is as bright as a Taiwanese supernovae, the supernovae that we use for cosmology. And finally, another important point is the explosion are spherical, and this can be derived by polarization measurement or by studying the profile of the nebulal lines of oxygen and iron during the nebular stages. And this is not a surprise, because even when we study core collapse supernovae associated that are not associated with gamma-ray burst, well, we discover that most of them occur in aspherical explosions. This result in basically the most important consequences for this spherical explosion is the fact that the quest for kinetic energy decrease dramatically, even to 70%. Still, the kinetic energy associated with supernova, gamma-ray burst supernova is still quite large, about 10 times what is observed in standard core collapse supernovae. Sorry, can you just give me 1 minute, because I have a problem here.
Maybe you can pick the slides and start the screen sharing from that slide.
Yes, I will. Wait a minute. Can you see this slide now?
Yes.
Sorry, wait a minute. Okay. So now let's go to the second item. What's progenitors? Well, supernovae occurs in any type of galaxies, from spiral to lenticular and ellipticals, but those are only Taiwanese. What about Taiwan BC? Well, they occur only in spiral and irregular galaxies. And this this make an easy suggestion that they are associated with massive stars. And how we can derive the masses of this of these supernovae? Well, through the collection of series of spectra and through the photometric follow-up, well, then we can build this series of spectra that you see at your left, the light curve that you see at your right. Then, let's say theoretical colleagues prepare a set of synthetic spectra that they compare with the observed spectra at different stages, close to maximum light and at nebular stages. And then they also prepare synthetic light curves that they compare with the observed one. And at this point, when the match is satisfactory enough, well, they come out with the mass of the progenitor stars that you see are of the order between, let's say, 25 and 50 solar masses. These, of course, come from, these last slides illustrates enough why a few moments ago I was telling you that we need to observe nearby objects to make this kind of measurement, to take from the data the most that we can. We can do that with faraway objects, simply, for example, because we don't have the chance to follow an object during the nebular stages if this is a cosmological distances. And the same for the light curves. If the object is far, we can observe just at the peak, but certainly not during the later stages. However, we can derive, let's say, still an important piece of information by studying from a statistical point of view the GRB supernova in faraway galaxies. And now I will not go into details as normally I do for this on this topic. Just as I have summarized here the result. At your left, you see typical host galaxies of standard core collapse supernova, and you see that they are, as expected, spirals, but let's say well-designed spirals. On the other hand, on your right side, you see the host of gamma ray burst and supernovae gamma ray burst, and they are mostly irregular and present what we call disturbed morphologies. And the conclusion is that type 1c and long duration gamma ray burst erupt in the brightest region of their host galaxies. And what does it mean? That the brightest regions of the galaxies are star formation regions. So the progenitor gamma ray bursts are so massive, basically, that so their lifetime on the main sequence is so short that they have no time to drift away, to drift apart from the place where they were born. And so basically they are born and die in the same place. And this is, I mean, another important piece of observation based on not only half a dozen of objects, but dozens of objects. So from a statistical point of view, is more relevant, is relevant, not more relevant, or more relevant, is relevant that the progenitors of long duration gamma ray bursts are associated with the death of massive stars. What the size of a progenitor? Well, this was computed for the first time in 2006, taking advantage, of course, again, from gamma ray burst 060218, that was a nearby object, 0.033 is the redshift. And basically what you see was the black body component was decreasing in temperature with time as soon as it was increasing in size with time. And when you compare the radius with the time, you discover that this expansion occurs at 30,000 kilometers per second, which incidentally is the same expansion velocity that was measured by Nando Patat for the ejecta of 98 PW. And so when you extrapolate back here we are 100 seconds after the event, and here we have an upper limit to the size of the progenitor. That is 4 times 10 to 11 centimeters. And this compare this way with the progenitor of core collapse supernovae. For standard type 2 supernovae, let's say the standard type 2 plateau, for people that are familiar with the jargon of the supernova jargon, this means that the typical progenitor is a red supergiant, characterized by a radius of 4 times 10 to the 13 centimeter. The progenitor of 87A was a blue supergiant, 10 times smaller, 4 times 10 to the 12 centimeters. So the radius of the progenitor supernova 2006 AJ associated with the gamma ray burst is basically is a Wolf-Rayet star, characterized by a very small radius, 4 times 10 to 11 centimeters. Basically, is a carbon-oxygen core, for example. Now, what is the rate of long-duration gamma ray burst? Rate for gigaparsec cube per year. Well, there are several measurements, and let's say the most recent, based on GBM, Batts, and Swift, are collected here in this pink column. And when you put all together this and consider in the proper way the uncertainty associated, you will you derive a rate of the order of 0.7 gamma ray burst per gigaparsec cube per year, with a factor of 2 uncertainty associated, as you can see from this plot. And then you compare this with the rate of 1 BC supernova. And the rate is can be derived from the 2 classical survey, the Asiago survey, that also include recent, with the paper by Maria Teresa Botticella, include the most recent observation carried out with VST, and the leak survey. Again, you put all together and you find a rate of 1 BC that is ranging between 2.2 times 10 to the 4 up to 3 times 10 to the 4 Taiwan BC supernova per gigaparsec cube per year. So you take the average value, and now you have to compare this rate of gamma ray burst with the rate of supernova 1bc. But before doing that, well, we have to take into account the possibility that these gamma ray burst, this event, are beam. And now also here,
excuse me, Massimo.
Yes,
Sorry, Jorge. Just to clarify one point, this GRB rate includes the low luminosity GRBs or not?
yes, all of them. Hello?
Yes, okay, thank you.
Okay, yes, but consider when you do this, rate of 1bc over rate of gamma ray burst, this rate of 1bc is a local rate of supernovae. So necessary this, I mean, yes, guy, thanks for your question, because if it is obvious for 1bc supernova that this is a local rate, since for gamma ray burst is a cosmological population of objects, that could be confusing. But yes, this is a gamma ray burst, is local, so include also the low luminosity. Thanks for your question. So now there is the possibility, we will see some details this in a few slides, that these objects are beam. However, there are a number of measurements for these beaming factors, so basically for these beaming angles. And this doesn't correspond to, in my opinion at least, it doesn't correspond going from 4 degrees up to angles that are even larger than 30 degrees. So they are almost isotropic, basically. This is not representative of uncertainties, but this is representative of the fact that these guys are beam in different ways. And probably, but this fact has not been is still investigated sufficiently, in my opinion, from a theoretical point of view, probably this beaming correlate with the energetic of the event. Anyway, when you consider this range of beaming factors, you derive a ratio between gamma ray, long duration gamma ray burst and 1bc supernovae that is in the range 1.5, 0.02. Now, GRBs are very rare phenomena. This is the first, let's say, conclusion that maybe could be classified as a trivial, but it is not, because it is posing an important question. When you consider this gamma ray burst over Taiwan BC supernovae at 1.5%, and this is the most conservative value, so the largest one, and you consider that the ratio between 1bc over core collapse is 0.30, is 30% basically. And this comes from the Asiago and Leaks survey. And you put all this together, you find that the gamma ray burst over core collapse supernova ratio is smaller than 0.005. It could be smaller or much smaller, according if you go to you get this the 0.02 value for this ratio. On the other hand, when you consider Salpeter IMF, a simple assumption, so you compare the number of progenitor of gamma ray burst supernovae that go, let's say, between 30 solar masses up to 120, and with all the family of progenitor stars, massive progenitor stars that can produce a core collapse supernova between 8 and 120 solar masses, you find that this ratio is 0.05. And so 5%. And when you compare this number here with this number, That's why I was saying at the beginning that when I say gamma ray bursts are very rare phenomena, is not a trivial statement. What causes some small fraction of core collapse supernovae to produce observable gamma ray bursts, while the majority do not? This is a question that is, I presented my slides in the last 15 years, and still we don't have an answer. Obviously, we can approach the answer by considering that that the spatial conditions are requested to massive stars, to progenitor of gamma ray burst, to massive star to become progenitor of gamma ray burst. We have seen to be massive between 30 and 50 solar masses. The hydrogen and helium envelopes have to be lost before the gravitational collapse of the core. So the gamma ray burst progenitors of Wolf-Rayet, as we have observed, so as observation have proven. We have from observation also another important condition, that the explosion has to be asymmetric. Then an important point is the environment. These guys like to explode in low metallicity environments. And this is well represented by this plot where you see this luminosity here versus metallicity plot for 53,000 galaxies of the Sloan Digital Sky Survey. The green area represent the 2 and 3 sigma confidence level. And as you see, when you look at the blue and red and also triangle, square, black square. So all these objects are connected with the gamma ray burst of subluminous long duration gamma ray burst. The blue are cosmological, the square are 1C, and you can see immediately from a simple glance to this plot that they tend to stay in the region characterized by low metallicities. Another important point is binarity. It is well known from stellar evolutions that most of massive stars are in binary system. According to Klaus Leiterer, I remember one of his talk in I think 2016, 2017. I remember he stated that 70% of massive stars are binaries. And so, since the progenitor of long duration gamma ray burst are massive stars, statistically, we have to conclude that most of progenitors of long duration gamma ray burst are binaries. And this concept has been elaborated, I think, starting from 2005 during the Marshall-Grossman meeting in Berlin by Ruffini and all the collaborators, and it is called, that they call this binary hypernova scenario. And this is the only theoretical, the only model that takes full advantage of the fact that most of progenitor of long duration gamma ray burst has to be in binary systems. I found a very, very, let's say, very clear because it's concise, but all the important points are mentioned. This brief review on binary driven hypernova that has been published very recently by the Jorge and all the rest of the gang, Pescara gang. One important point that was observed in 2014 by Melandri and collaborators was that the luminosity of at the peak luminosity of supernovae apparently doesn't correlate with the gamma budget, with the energy of the gamma reburst. So as you see here, while the gamma budget covers several orders of magnitude, the luminosity of gamma reburst vary by at most the peak luminosity of gamma reburst supernovae vary by a factor of 4 or 5. And this fact provides evidence for a lack of correlation between the prompt emission and associated supernova properties. But I have to say that this important plot was not really exploited in that paper because it was not clear how to interpret this. Because 6 years, 8 years ago, probably we were not ready to give the right interpretation of this. And this is the modern, the updated figure that has been produced in Pescara. Is produced just in these days, and show exactly, of course, illustrate the same concept, but with a more robust statistical basis. And you see again here that the luminosity of supernovae is within a factor of 10, while the isotropic energy of the associated gamma reburst span about 7 orders of magnitude. And this is a really strong conclusion. Even if we consider the possibility that these gamma rebursts are beam, and this, okay, there are evidence for beaming, and in some gamma rebursts, this evidence is provided by the detection of a change, a chromatic change in the slope of the afterglows. However, there are many gamma rebursts where this achromatic break has not been observed, and this implies that they have a very their emission is characterized by very large angle, or maybe they are isotropical. So even if you consider the beaming, well, when you apply this, instead of 10 to the 54, you can decrease the question for energy to 10 to the 52. Still, we have a full 5 order of magnitude, while the luminosity at the peak of associated supernovae vary at the most within a factor of 10. So the conclusion is that the luminosity of the associated supernova remains constant within a factor of 10, while the energy of the associated gamma reburst varies within several orders of magnitude. And I have my image is this one. The tracks, the rail tracks. Why? I have explained it. I try to explain this just below. The link between supernova and gamma reburst phenomena is limited to the trigger, in the sense that it is true that the supernova start the show, but then the causality link between the two phenomena seems to vanish, and don't have more consequences. The supernova and gamma ray burst don't have don't show any subsequent feedback. So they start from the same station, but they proceed parallel each other. I think that someone after me will go to talk about this deeper. The other point is we should take into account is the high rotation. And this is important because if there are jets, well, these jets have to be fed by something, and this is the angular momentum of the progenitor. Well, in case the progenitor star go through the so-called normal evolution, that means the star on the main sequence, then the envelope, then the star lose the envelope, so lose also angular momentum. Well, at the end, they can explode, of course, as a core collapse supernova, but they are not anymore able to feed the gamma burst jets. So while to overcome this drawback, has been elaborated in the years of this chemically homogeneous evolution by a number of theoreticians that I reported here, a few people of them, if you want to go deeper on this. And this implies that if the star rotates fast enough, this is the basic concept, this allows the star to avoid the red supergiant stage and to become directly a Wolf-Rayet. So in this way, the progenitor star is able to retain most of angular momentum in the core because the huge envelope is not formed and the huge envelope so is not lost. Observation of core collapse supernova revealed the existence of a continuum of properties among the different core collapse classes. So I have mentioned during my talk a lot of these classes, 1A, sorry, type 2, 1B, 1C, 1BC, type 2. Maybe I didn't have time to mention type 2N, type 2B, but never mind. Well, in fact, these classes are, let's say, well, I don't need to change my words. I have already written here. I have already reported here what the observations suggest. That these core collapse supernovae show that there are not really classes, separated classes, but a continuum of properties moving from one class to the following one. So, for example, type 2 start with solar masses with the progenitor having 8 to 10 solar masses, 1B 30 solar masses, and gamma ray supernova 40 solar masses. So that the mass or the hydrogen envelope for type 2 is between 1 and 15 solar masses. For 1B is 10 to minus 1, 10 to minus 3, and for gamma ray supernovae is certainly much smaller than 10 to minus 5. All of these are numbers that come from observations, what you observe here. The polarization from 1% for type 2, that means almost spherical explosion, to 4%, that means an oblate explosion, so a spherical. The rate, of course, is, as we have seen in details, decreased dramatically from type 2 supernovae to gamma ray burst supernovae, but the kinetic energy increase, the kinetic energy associated with the ejecta, and also the radius decrease. The other important point is what produced the observed variety in long duration gamma ray burst phenomenology. We have seen that these gamma ray burst supernovae, sorry, these gamma ray bursts represent, they are very rare. So we observe a few objects, but in spite of that, we are able to observe a large variety. High luminosity gamma ray burst associated with bright 1bc, so supernovae. Low luminosity associated with bright 1bc. Then we have also low luminosity gamma ray burst associated with faint 1bc. Then we have hypernovae without a gamma ray burst. This introduce an important point that I have no time to mention, the so-called cocoon supernovae, but I think that some other speakers will talk about this. Then we have a gamma ray burst, long duration gamma ray burst without a bright supernova or without supernova at all. And this is the case of, for example, of the recent gamma ray burst 2011A, very similar to what was observed in gamma ray burst 06-06-14, where people claim the possibility that there is a kilonova associated with this event. Then we have gamma ray burst associated with standard 1bc supernova. A few cases, but there are at least two objects. And when you have a very long duration gamma ray burst associated with bright 1bc and very long duration gamma ray burst associated with superluminous supernovae. So how we can explain this variety? Okay, this is one of the challenge, in my opinion, that the theory teachers have to deal with. However, I think, again, the binary hypernova scenario has the possibility through the interplane between the separation of the objects, between the considering different accretion masses or different mass of neutron star or whatever you have in this model, you can play and you can probably explain most of this variety. Okay, I will stop here.
Okay, thank you very much.
Thank you for the attention. Thank you.
Okay, so I think we have room for 2 minutes of a couple of questions. And before the question, I have a remark. In one of your first slides, Massimo, you were saying about 60 GRBs associated with supernovae. And actually, with one of the students, we were working on like a large catalog of GRB supernovae associated, and we counted 69 with precise association. And with 109, if we consider the full sample, but many of them have poor association because of the, sometimes it was just the location that was not well determined. So I just want to point here. And also, I would like to mention, there is a question by Jorge, so maybe I'll leave the room to Jorge and then to Biagio. Thanks.
Thank you, Maria Giovanna. As I said, I was taking the paper by Kovacevic, and then I have estimated about 10 of these associated were known with the sufficient data, but probably, not probably, for sure they are more. So today are about 17 with, 70. Okay, thanks.
Okay, thank you, Maria Giovanna, for allowing me to Right, this question. Oh, first of all, Massimo, thank you for all this material. That is really nice. There are many questions, and as you said, in our model we can give an answer to some of these questions.
Yes.
Not to all of them at the moment, but we will take care of them. But my question comes again to the rate of about 1 gigaparsec cube per year. In our work of 2016, we made an estimate of the GRB rate for the low luminosity, so for the bars with isotropic energy smaller than 10 to the 52 erg, and we end with a higher rate. And the rate of 1 bars per gigaparsec cube per year was for us in agreement with the range in redshift between 0.7 and 1, while at a lower redshift we have a higher value between 30 and 200. So I would like that we check together this, okay? Because apparently we use the same method that you use, but we have different numbers for the low luminosity ones. So I would like that we, at some moment, we check these numbers together.
Yes, Jorge, but sorry, if I understand well, you say that one gigaparsec cube per year, that was your rate, in your local rate. Did I understand well?
Between redshift 0.7 and 1.
No, the local one.
No, local was higher for low luminosity GRBs, was higher. Well, much higher, between 30 and 200.
Oh, look, this is okay. This is these are the observer rate Z0, as you see here. From I was not the author of this. I mean, but I agree with this number because we have computed in different way. However, Z0 is a 0.5, 1 is 0.6, and this comes from 3 different instruments.
Yes, for local.
Yes,
at Z equal to 0, we agree with this value for the bars with energies larger than 10 to the 52. We fully agree with this number, but for the lower energy sources, we have a different rate. This is the point that I would like that we check together at some point.
Okay.
And maybe I would like to add something also in relation to the talk that was given yesterday on Monday by Vahe Petrosian about the problem that we still face about the GRB rate versus star formation rate. He was presenting the study of all the sample of long gamma ray bursts, including also the ones associated with supernovae. So if we don't correct for selection biases, the rate may be also different. So I also want to bring this up, that for high redshift correction may matter. Okay, and I think there is also a question by Biagio. So Biagio, please.
Yeah. Thank you, Professor Dainotti, and thank you, Professor Della Valle, for this talk that was really interesting. First of all, I wanted to say that I agree with the fact that prompt properties of GRBs are not likely to be associated easily with the supernovae properties. Indeed, we recently submitted a research work of correlations, of unbiased correlations between the properties of GRBs and supernovae, and especially we focus on the afterglow properties, and we will be happy in the next months to update you on these results. Anyway, I had a question about the standardizability of GRB supernovae, because in a famous paper of Zaccano of 2014, he stated how the GRB supernovae can be considered as a standardized candle in light of a stretch factor relation, which is very similar to supernova 1A. I would like to know what do you think about this relation, and according to this relation, how many events we need for that relation to be used as a tool for standardizing GRB supernova, and also to use them as cosmological probes. Thank you. Okay,
I think I remember that suggestion that to use the supernovae associated with long duration gamma ray burst as a standardizable standard candle. But I mean, now if you read the last paper on cosmology, on observational cosmology, we are talking about accuracy of the order of a few percent, 2%, typically, if you go to the last paper by Adam Rees, for example. And I was looking happy to this possibility, but I didn't come out with something really significant. I mean, if you look at a plot like this, obviously, if you compare the luminosity of supernovae with this with the isotropic energy of gamma ray burst, well, yes, it is a relatively to the isotropic energy of gamma ray burst, this supernova can be considered, let's say, almost candle, because they vary the luminosity, as you see here, where you have a little bit of statistics, by a factor of 10. Yes, but a factor of 10 is means a factor of 3 in distance, at least. And then even if you try to apply this correction for stretching, it doesn't work. It doesn't work to reach the accuracy that we need. Okay, so to me, is a blind way. I mean, I prefer using gamma ray burst for cosmology, not the supernova associated with gamma ray burst. Sorry, I have to tell to Jorge that he is right and I was wrong when I answered to his question during my talk, because I was looking now to my paper with Daphne Guetta in 2007, and in fact we found a much larger rate for low luminosity gamma ray burst. And what I've reported here, obviously, is the rate of gamma ray burst, the so-called cosmological gamma ray burst. Okay.
Okay.
So,
thank
so
you.
sorry, but if you go and you look at the Guetta in the Della Valle 2007 is an APJ letter, you will find a higher, the higher value of gamma ray burst, low luminosity. I was wrong.
So
yes.
our numbers perfectly agree.
Yes,
so
yes,
yeah.
Absolutely. So, thank you, Jorge. Thank you.
Thank you, Professor, for
thank you to
your
you.
explanation.
Thank you very much. I have just one small comment on the Cano relation, because when we updated the sample with many more GRBs, we couldn't recover the same strength of the correlation. So that's why Biagio was asking about that.
Yes.
So
sorry, excuse me, I didn't understand. You could or you couldn't?
We could not.
You could not. So
with
okay.
the same strength of the correlation. So we were wondering whether or not was mainly due to the paucity of the sample. So that's why I think Biagio was.
No. I was just looking at the beginning of this story, and I didn't have really a good feedback, and so I didn't go further, because I think it's not. It is not the case. Yes. Okay.
Okay. Thank you very much.
Thank you.
Thank you. Again.
Thank you, Maria Giovanni.
And we will have to move to the next speaker of today's session, who is Rahim Moradi, and we'll speak about the nature of the ultra-relativistic prompt emission phase of GRB 190114C and 180720B.
Hello, can you hear me?
Yes, thanks.
Good morning. Let me share my screen. Okay. Principal, you should see my screen.
Yes, we can see your screen.
Okay, good.
Thank you.
Hello, everybody. Today I'm going to talk about two specific GRBs within binary driven hypernova, namely GRB 180720b and GRB 190114c, which, thanks to their high quality observational data ranging from radio to sub-TEV emission, they are good examples to test our GRB theories. Specifically, I will focus on the ultra-relativistic prompt emission phase of this GRB, which happens in the early phase of the prompt emission, around less than 10 seconds of the early phase of the prompt emission. BDHN has different episodes that thanks to its binarity nature, we can understand these different episodes. But here, as I said, I will only focus on this early phase and will explain a bit about other episodes. This is in collaboration with Ikran people that also am part of this work, presenting it.
The dates 16th, 18th of May are wrong. Is between 4th of July
Yeah,
and
wrongly.
14 July. Yes.
Yeah.
It's updated to
okay.
today. It's updated to today.
Yes. So this is the real date. So the first case is GRB 180720b, and as you can see, it, as I mentioned, it has data from radio, optical, Hess emission, sub-TEV emission, X-ray, gamma ray, and all range of the set of data. It is in a redshift of 0.65, and it has isotropic energy of 10 to 53, which I will explain what are these different color in the picture later during the talk. But this is just to show that how these GRBs are rich in their data. Also, this is GRB 190114c, and this has another good feature that it shows the rise of optical supernova at around 18 days of the burst, 10 to 6 seconds in the rest frame. It shows also TEV emission, optical, radio, and JEV, and also prompt emission. This was one of the first GRBs, not the first one, but one of the prominent GRBs that we studied a BDHN model, because we also predicted based on the energetic and based on the observed data, high resolution observed data, we could predict the occurrence of the optical supernova bump around 19 days after the burst, which was indeed observed, and recently the full comprehensive paper about this supernova event was published by Melandri et al., which we have seen several talk about it during the Marcel Grossman and other meeting of ICRAN. So in short, if I want to say something about binary driven hypernova, which in this talk only I will focus on the type 1 of this binary system. This system has 3 pillars: black hole, supernova, and neutron star. Binary binary of a carbon-oxygen core supernova explosion. It will have its supernova ejecta pouring out of the system, out of the central object, and this central object will be a new neutron star, which we call it for sure new neutron star, and this new we showed in Latin new neutron star later on. We'll show. What happened for this system? This system can have different a binary period, can have different binary separation, and all these three parameters are this model in general, binary driven hypernova, can tell us what can happen for this binary system. For example, its binary period is around 5 minutes. The supernova ejecta can accrete enough mass to the companion neutron star, which you can see in the right side of the supernova explosion. Star with the three components of binary. Can you hear me? Because then my
Yes, we can hear you. Thank you.
It's this system will be left. I emphasize again. Here is binary driven hypernova. One system will be left with three main components. At the center of supernova explosion, we'll have the new neutron star. Then we'll have supernova ejecta, and as a companion, we'll have black hole, which is formed out of hypercritical accretion onto the companion neutron star. If this hypercritical accretion doesn't happen, black hole will not be formed, and we'll have another system which we call type 2. And instead of black hole, we have more massive neutron star. This will be comprehensively presented today and next day by I don't know, maybe Jorge or Wan Yu and other people of the group. So I don't go through the detail of this model anymore. So here, my focus will be only on the interaction of supernova ejecta onto with the black hole, with the companion neutron star. And what is this says? This interplay of these three components will lead to different episodes of the system. First, we'll have black hole formation, which we call it in this system black hole rise. Then, on the other hand, we have the fallback accretion of neutron star, which has been extensively studied and recently studied by our group, Jorge, Laura, Professor Pina, all the people of the group. They have studied the fallback accretion on the neutron star, which will be seen in the prompt as a new neutron star rise. Then we have, when black hole is formed, it's natural that it accretes majority of mass around it. So black hole will live inside the ejecta with a cavity around. It's like a void around it. And also this has some observational effect, which I will mention. In short, if I want to say something about this, the origin of the observation photon of different episodes, apart from neutron star rise, I focus on the black hole rise. First, we have a black hole in presence of magnetic field. Then we'll have the optically thick E plus E minus around the black hole, which the which will be self-accelerated because of its high internal pressure, which this is the GRB. This, because it's optically thick, it needs to propagate with high gamma factor, which we call, that's why we call ultra-relativistic ground emission phase, reaches distances 10 to 11, 10 to 13 centimeter, and emits photon. But this is not the whole story. We will see only this part in this UP phase in part of the system.
Okay, we have a problem with connection. I can't hear. I don't know if it is only from my side.
No, me too. I cannot
Also
hear.
from your
The
side.
slide is stuck.
So, Rahim, can you hear us? Okay, I don't know how we
System
can.
manager. System manager.
Can you hear me now?
Yes, yes, we can hear you. Yes, please continue from where you left. Maybe if you have problem with connection, you can stop your video. Probably this can help. So now we can see you, but we cannot see the slides. And you are muted, Rahim. You are muted. So if you can unmute yourself.
Can you hear me now? Sorry,
Yes,
there was
yes,
a problem
now.
with the Wi-Fi connection.
Yes, now we can hear you. Thank you. Thanks.
Okay. Hope this problem doesn't happen again. Okay. So let me start this slide again. I don't know where I was interrupted. Can you hear me now? Hello?
Yes, yes, we can hear and see.
Okay, good. So as I said, there is a black hole formation, which I explained. There would be optically thick E plus E minus plasma around it, and due to itself, its internal pressure, it will self-accelerate, and will at the transparency point with high gamma factor, which we call, that's why we call it ultra-relativistic ground emission phase, we'll see the UP phase, ultra-relativistic ground emission phase, at the transparency point. But this is not the end of the story, because we have supernova ejecta around. The interaction of this E plus E minus baryon with the internal part of the cavity will lead to the cavity emission from the cavity, and decelerating of this highly ultra-relativistic E plus E minus plasma baryon inside the supernova ejecta, and radiation almost in the outer layer of the supernova ejecta around 10 to 13, 10 to 12 centimeter will lead to the hard and soft X-ray flare. So this thing that I said, the episode 1 and 3 are the ultra-relativistic ground emission phase, then it will go to interact with the inner part of the cavity, episode 4, and episodes 5 and 6 are the hard and soft X-ray flares. Okay, this is a short description of the model, and as I told, I will only focus on the early phase, episode 1 and 3, which is UP phase. And this was the case of 1807-20B, and this is the case of 1901-14C. So now let's go to the main topic of this talk, which is the UP phase. How observationally we find this UP phase? We say that at the transparency point of this E plus E minus plasma, we expect some thermal component. So the moment that we find the thermal component in the observation, we marked it as a beginning of the ultra-relativity prompt emission phase. But something interesting happened, that if we find high resolution data or high quality data, which also the later generation of future generation of the satellites detector will help us to confirm this more, is that as you can see, A is the like time interval from 1 to 4 seconds. Then we divide this time interval by 2, then by 4, and always to the 5th iteration, we always find these thermal components. So this raises a question that what is the true level of this, what is the true resolution of this observation? Is this, let's say, self-similarity in the spectrum, which I will explain. Okay. As I said, we have accretion to companion neutron star, then black hole forms. Black hole forms, this neutron star has its own around 10 to 13 Gauss. Then we'll have this torus-like around it. We'll amplify the magnetic field to 10 to 14 Gauss. Also, there are many simulation which will support this idea that finally we will be left with almost collimated magnetic field along the axis of the black hole, and the black hole, rotating black hole, which is Kerr. So the nearest mathematical solution to this, that was already studied in the literature, was Wald-Papapetrov mathematical solution. What does it say? This is very interesting solution that almost after 40 years, it gains attention by the astrophysical community with many groups that can serve as a inner engine of AGN or black holes or GRBs. We have a Kerr black hole inside a uniform magnetic field. Let's say this is the simplified assumption, and I will show later how this simplified assumption is the perturbative level of their comprehensive solution. It will rotate, it will induce electromagnetic field. And the main characteristic of this is that the second Maxwell invariant is not zero, E dot B is not zero, so this E that is induced in the system is a real E, so a real electric field. So this real electric field can induce, it is not induced, it can be responsible for many astrophysical phenomena like accelerating particle or producing pair via magnetic pair production or via other things. The main characteristic is that the interaction of the rotational energy, rotation with the surrounding magnetic field will lead to this Q effective of 2B0J. As you can see, B0 is the strength of uniform magnetic field. J is the rotational angular momentum of the black hole. And as it's obvious, it tells us that the origin of charging black hole, which is a mystery in the nature, is this kind of interaction of the rotation and the magnetic field. And this has very interesting aspects that I will represent them. And what is the idea is that it's very pure mathematical idea, I will not go through it, is that the Killing vector in vacuum space-time generate Maxwell there is a problem in that space-time maxwell field. So and this system has two killing vector of the axial killing vector and the time lag killing vector. Finally, it will leave us with this electromagnetic field as a, let's say, perturbative for magnetic field, not comparable to the mass of black hole. When I say the energy of the electromagnetic field, which around less than 10 to 16 Gauss, still this solution can be used. Why this solution might work is that first, E dot B is not zero, so it's a good news that always there is a problem how we can accelerate particle, how we can produce pair, how we can use this quantum effect of Schrödinger, which always needs a non-vanishing electric field. And this can be used for studying the ultra-relativistic prompt emission phase, the origin of E plus E minus plasma around the black hole, and how particle will be accelerated around the black hole. Okay, the early study of this system with the extreme case of black hole mass charge to mass ratio, which is extreme, it can be only considered as theoretical work, is that for a black hole mass of 10 solar mass and extreme case of charge to mass ratio of 0.1, around the black hole, when we have this high electromagnetic field, there would be E plus E minus because of the Schrödinger pair production. The total number is around 10 to 58. And this will lead a very high, the optically thick region that for sure radiation cannot happen there, but it can be considered as the source of energy that will produce at the transparency point this radiation. And the story is like this. We have this optically thick region. It will explode. The explosion is this part because of high internal pressure. Really, it's such a high number density and number of electrons around this system will make the explosion happen. And this is the, let's say, if you want to say the real GRB, that it will expand and the radiation that we will see happen at around 10 to 10 centimeter to 10 to 13 centimeter, but it depends on the parameter of the system. And this idea was first proposed by Damour and Ruffini, then Ruffini, Wilson, Schoer, Salamonson. They developed the idea of expanding shell. And this work was, at that moment, the origin of charged black hole was not known. They considered Kerr-Newman black hole. But now with more realistic system, we have this more realistic structure, we will study this effect. Okay, as I said, before going on this, around the black hole, this purple region, we call it Diado region. In the case of Kerr-Newman, it has a torus, like we call it Diado torus, but in the case of Wald-Papa-Petro solution, it has different type, which is not the well-known mathematical figure, mathematical object. We call it Diado region for simplicity. And this has been shown by some theorem that this solution of Wald-Papa-Petro at the perturbative level, what perturbative means, low magnetic field, by low, still 10 to 14 Gauss is low comparing to the whole energy of the system. And for spin parameter of the system less than 0.6, with good approximation, this can be approximated by the Kerr-Newman metric. So thanks to the, as I said, work started by Damour, Ruffini, Wilson, Salomonson, Schoe, and recently Cherubini, Rueda, and Ruffini, I think 2009, they introduced the formalism to calculate the energy of this region around the black hole that has overcritical electric field and this energy of this total pair around the pairs around the black hole. And as you can see, the only thing that we do is that instead of Q of Kerr-Newman, we use our effective charge to B0J, and we calculate the energy of the other region around the black hole. We calculate the width of the this system, which are needed for calculating the properties at transparency point. And this is the simple formulation of this system. We have this thermalized system around the black hole by doing some ultra-relativistic transformation and demanding that at the radius of transparency, we should have the optically thick system. And in addition, there is a baryon load matter around the black hole, baryon load that will be swept by this E plus E minus and will be carried till the moment of transparency. Naturally, with kinetic energy of the system, transparency condition, and the relativistic transformation, we can find the properties at transparency, namely the baryon load, the radius of transparency, and all necessary parameters of the transparency condition. And after writing this formalism, the only thing that is needed, the isotropic energy, the observed value of the black body, and the width of this E plus E minus plasma region around the black hole. Before going on, I should mention something very important, that each E plus E minus that occurs around the black hole and accelerate, it takes a part of rotational energy of the black hole. For this case, when we have B0 around 10 to 14 Gauss, this delta J is almost 10 to minus 9 of the original angular momentum. So one expanding E plus E minus plasma plus baryon, which we call pair electromagnetic baryon pulse, PEM pulse for simplicity, will go, it will take, as it's in energy, it will take part of rotational energy of black hole. What will happen? Black hole will be left with new effective charge or new effective electric field that again will produce new region of in presence of its original magnetic field. Again, it will produce a new E plus E minus region, the other region around the black hole. And again, it will accelerate. So we will have many of these PEM pulses, one after another will reach to the transparency. And this will happen till the moment that black hole the black hole electric field is not overcritical anymore. So as the absolute lower limit of magnetic field, electric field is that at the end of UP phase, which we will mark observationally, where the observed black body is, over, there is no observed black body anymore, we will see that E goes under critical and this process stops. So the central engine for producing all this episode that will last for like 100 seconds, 200 seconds, is at work for some seconds, but the expansion plays also important role. So these are the observational, as I showed you, these are the observational, rank plot is here, but no, it doesn't matter. These are the observational properties of the UP phase that we observed thanks to the good work of Liang Li. He did fully statistical spectral analysis of the system. He found this black body that should be significant, statistically all confidence black body, meaningful black body, statistically, I mean. And thanks to this high resolution data analysis, we can calculate what is the radius of transparency of this, what is this PEM pulses, what is their gamma and other parameters. But before going on, I should mention, before showing the result, I should mention that in our system, black hole is made from the neutron star hypercritical to the accretion to the neutron star, and the neutron star will reach its critical mass. We assume that this second m square j square plus m irreducible square is the famous Kirsidulu Hawking mass that we use for the black hole. And you can see we cannot, we assume that extractable energy of the black hole is total mass minus the irreducible mass of system. As you can see, this is a function of m and alpha, so it's one equation that we cannot deduce alpha and mass from it. So good that we have in our PDHN model from the neutron star critical mass, we will have the black hole formation, the moment of black hole formation. So we need another mass for the critical mass of neutron star, which is also a function of alpha and m. So by requiring that mass must be larger or equal to critical mass of the neutron star, we will calculate the mass and spin of black hole. For example, for the case of 180720b is around 3 solar masses. For other case 2.4, it's very near to the critical mass of neutron star. So, and for calculating the evolution of mass and spin, it's easy from the black hole mass formula. We demand that luminosity of UP phase, which we for simplicity we consider the power law, is the E over dt of the black hole mass. So by having the initial mass from the neutron star, we can calculate the evolution of spin and mass of the black hole at different times. This is shown for GRB 180720b that its spin starts from 0.6, at the end of UP it goes to 0.54, showing that the black hole spin and black hole mass are decreasing because of the radiation of the ultra-relativistic prompt emission phase. And these are the results for 180720b. And as you can see, the this up left is the E over E critical electric field. As you can see at the end of UP phase, electric field is equal to critical field. So black hole Schwinger formula doesn't work. It's not at work anymore. So UP phase is done. And the energy of each PEM pulse is around 10 to 45, 44 ergs. the width of each pulse is around 10 to 5 centimeters, so it's around 2 Schwarzschild, 2 horizon radius. The radius of transparency is around 10 to 10 centimeter, and the gamma factor is around 50, let's say 50 is the gamma factor of this. And this is also for spectral analysis of 1901-14C. Again, thanks to work of Liang, we found this high resolution thermal thanks to high resolution data, we found the thermal components. And as I said, this is necessary, observation is necessary to find out the parameter of the UPE phase. And for sure, the next generation of the satellites detector will help us to put more constraint on this value that we have. So this value that we have, like around 10 to 9 PEM pulse during 10 seconds is kind of the upper limit. They can be a bit less, but this is the best that we can do. Only the high resolution data analysis we can tell us at which level this thermal component starts to be observed. And again, this is the same parameter of for the GRB 1901-14C, and as you can see, the same behavior they have during the UPE phase. And if I want to conclude, is that the inner engine is this system that I introduced, perpetual wall solution plus very ionized matter around. And black hole is not charged by the charged black hole in the system are on the nature are effective charge. That GRB is the, if I want to say something about GRB is the outcome of charging and discharging of this effective charge of the system that this is nature doesn't like charge. Always it wants to discharge, and GRB is the outcome of this dislike of nature. And it will give us many good ideas about the black hole physics, because around the black hole, we cannot, around this astrophysical black hole, we cannot have photons. Whatever is there, it would be the optical tick. So the definition of black hole horizon, photon can escape to infinity. All this, in my opinion, should be written based on the real astrophysical systems that are at work in the nature. Thank you.
Thank you very much for your nice talk. And I know that we have like just a few minutes for questions. So now the room is open for questions or comments.
Well, I would like first of all to congratulate Rahim to have made this very difficult and simple and complex presentation.
Thank you.
I think every word he has been using, the fact that the energy of is due to the rotational energy of the black hole, that is vacuum polarization, that there is acceleration process all the way to gamma, are a very new result on repetitive time scale, which can be of the order of 10⁻⁹ seconds or more. This is a new concept. Fortunately, all this material has been published. It's not trivial. I think it's the most difficult problem ever addressed, maybe in theoretical physics, because it's a mixture between quantum, general relativity, and completely different from what has been done up to now looking at accretion of massive particles, which were introduced by long ago by the work of Wittwiller and on the accretion of massive particles around black hole and the emission of gravitational wave. When black holes are alive, and this is the message, they don't radiate gravitational waves, they radiate very high energy electrodynamical process of vacuum polarization. And the energy extraction appears mainly in the MEV, then in the JEV, but is the rotational energy of the black hole, which is the source of all this energy. And the process are new. They have been to study. They are published now. And is the very low density of plasma around the black hole which allow this process of vacuum polarization to occur. This is a new arena of theoretical physics. And I hope that this summary, which was really masterfully presented in this very complex way, is the key point. Rotational energy of the black hole extracted by the effective charge and on very, very time scale, new time scale, 10 minus 9 to 10 minus 14 seconds, repetitive, which occurs during the first 2 or 3 seconds of the UP phase. This is conceptually totally new and this modify the concept of jets. Jets are not needed. We just need vacuum polarization. I hope you agree on this point, Raim, and make maybe a conclusion remark. We cannot do more in little time, but again, everything is published. People have just to learn all this process which took 50 years to develop.
Thank you very much, Professor Ruffini, for your comment. So I think it's now, if there are no additional comments, remarks or questions, then I think
I have Maria Giovanna. May I just very short?
Yes.
Very
yes,
short.
Please, Jorgen. Yes, go ahead.
Very short. Just to tell you that today in the archive, there is a new article about a possible measurement of a very heavy neutron star with a mass between 2.2 and 2.5 solar masses with a best fit of 2.35 solar masses. So this is extremely connected with our calculations, with our estimates for the neutron star mass. So this is why I would like to point this out. This is actually agree with our estimates for the black hole mass and the equation of state that we use in our calculation. But I leave in the chat the link to the publication so everyone can go and see it. Thank you.
Thank you, Jorge. Thank you. This is really interesting.
Thank you very much, Jorge, for your comment.
Great news. And
okay, so now
the first time that we measure the mass of the black hole in GRB. People should realize that with great precision, and we have many cases. It's a new era. And we not only the mass, but also the spin. And all the electrodynamic involved. Okay.
Okay, so thank you again, and I think we move to Luca Izzo. So there was, sorry about that, there was a last-minute change of program. So please, Luca, the floor is yours, and I would recommend if you can stay on time, because then we have the lunch break.
No worries, I will be shorter than expected because I have a faculty meeting at 11 here. So
okay, perfect. Thank you.
Quick. Okay, can you see my slides?
Yes.
Okay, all right. Okay, good morning to everyone, and thank you very much for giving me the opportunity to present one of the research lines where I am personally involved within the context of currently operating high cadence optical survey as well as gamma ray detector, which is the search for jet cocoons in broadline supernova. This is indeed a topic that embraces two community. One is the supernova community and also the gamma ray, the GRB1, given that 1C broadline supernova is also the only supernova type with few exceptions, only one, that is associated to gamma ray bursts. For this reason, I will really do a very short introduction to GRB phenomenology, which is important for what I'm going to present in my talk, in particular to the class of long gamma ray burst. GRB can only be detected using space detectors, given the fact that given the high opacity of of the Earth atmosphere to high energy photons. And actually, we have a very good knowledge of GRB since the 90s, when satellites like BATSI and Beposac started to observe the gamma ray sky. And actually, thanks to BATSI, and then also with Beposac, with the detection of the redshift and the origin of the cosmological nature of GRBs, we know that GRBs have indeed a cosmological origin, but this was not very well clear before 90s. This is, gamma ray bursts are, we already had several talks about GRBs, just a brief recap of how they are, what is the phenomenology of gamma ray bursts. We have a first prompt emission, which is very regular and very variegate, where the emission is mainly concentrated in the gamma ray hard X-ray energy range from 10 to 10 keV from 1 MeV. You can see that the light curve is very distinct. This is a famous plot shown in many talks that has been made using BATSI light curve. We have different GRB events, like, for example, Fred spikes, fast rise and exponential decays, or very short spike, short GRBs, or irregular behavior with, in some cases, also precursor event. However, this is not actually the same. The situation is not mirrored in the X-ray and longer wavelength, where the emission is more smooth and can be also, sorry, because I'm receiving alerts. I'm just stopping my phone, where the emission is more smooth and the behavior can be in general classified in few classes, given that this emission is mainly due to the synchrotron emission. Actually, the synchrotron emission is mainly responsible for the afterglow, and it originates from the external shock, from the forward shock of the jet propagating into the circumstellar medium, circumburst medium, and the resulting spectrum actually can be very well characterized by a sequence of power law behavior, smoothly connected at specific break frequencies that can be easily computed using the formula of the synchrotron emission. I'm not going to talk more on the emission processes, just to say that GRBs have been historically classified in two classes, the long and short GRBs, where the main dividing line is characterized by a T90 duration of 2 seconds, where T90 is the time where 90% of the emission from gamma ray bursts in the gamma rays has been detected. And this classification is also is not only based on photometrical properties, but also the spectral emission distribution of photons as a function of energy shows a different characterization for short and long GRB events, with short GRBs being much harder than long events. And these evidence, in addition to the fact that short GRB have in general on average lower isotropic energy than long gamma ray burst event, led to enforced the idea proposed in the late 80s that short GRBs originated from the collapse of two compact stars, like two neutron stars, while long gamma ray burst originates in the collapse of a very massive and highly rotating star. But in both cases, we have the formation of a remnant, generally a black hole, but some people also have proposed a very highly magnetic neutron star. And this black hole can emit a highly collimated jet due to the accretion of the very dense material surrounding the remnant, leading to a highly collimated emission, whose evolution gives rise to the gamma ray emission by internal shock, and then with the interaction with the circumstellar medium to longer wavelength emission like the X-ray, optical, and radio emission. This talk I will mainly focus, of course, on the long GRB events. So now, several observational approaches pointed out that in the previous year, the fact that there is a possible connection between GRBs and the collapse of massive star. Indeed, the average isotropic energy emitted in a long GRBs is very similar to the kinetic energy measured from core collapse supernova. Moreover, long GRBs are generally observed very close to the brightest region of their host galaxies, which are generally bright star-forming regions. This means that GRBs generally explode, at least GRB progenitor, explode very close to the same region where they were born. And in these pictures, which was published almost 15 years ago, there is a small collection of few GRB host galaxies where you can see that the green cross represents the position of the long GRB, and apart from a few cases, they almost coincide with the bright region of their host galaxies. And the first clear, probably Massimo already talked about the classification of different supernova types. I did not, I arrived too late because I had the connection problem. I don't know if Massimo present all the different supernova types.
Yes, he did.
Okay, so just briefly mention that the class of supernova connected with the long gamma ray bars is of type 1c, which is generally due to whose progeny is generally a Wolf-Rayet of the carbon-oxygen type. But unlike normal type 1c supernova, in long gamma ray bars, we see typical absorption lines that are much broader and whose minimum and also the terminal velocity is at much higher velocity than typically observed in one normal type 1c supernova. This suggests indeed the presence of an additional central engine powering the emission of gamma ray bursts. And the first clear connection between a GRB and a supernova, was the famous event, or now can also be mentioned as the canonical example of supernova associated with gamma ray burst, 980425. This is still, despite it has been detected almost 25 years ago, it is still the closest GRB ever known, but however, it is a low luminous GRB with an isotropic energy emitted of 10 to 49 erg, unlike cosmological GRB where their isotropic energy is larger than 10 to the 51 erg. Another point that it was detected by Bazzi and Beppo-Sachs, and given that it was very close, the following optical follow-up led to the discovery of rising optical emission that was associated with the presence of a 1C broadline supernova a few days after the GRB detection. This is also one of the brightest supernovae associated with gamma ray bars. This can be explained with the large amount of nickel, 56 nickel decay, 56 nickel synthesized in the collapse, and this can be estimated from the nebular spectrum. We need to wait a few years after the 980425 to observe another spectroscopically identified supernova associated with the gamma ray bars. This is 30329, which, unlike the previous case, was a very bright gamma ray burst with an isotopic energy of 10 to the 53 erg. And the fact that it was so much bright, it also implied that its afterglow was equally bright. Indeed, in this plot, the central panel, we can see the optical R-band afterglow of this event. We can see a typical exponential decay that presented a sort of, a bump that have been associated with the presence of an underlying supernova. And in order to clearly identifying the presence of the supernova, people needed to subtract the afterglow X-ray component from the optical, given that the afterglow is simply a power law. So from X-ray observation, you can simply extrapolate the power law behavior, as we have seen that the synchrotron is simply a power law, to optical wavelengths, and then from the subtracted spectrum, people derived the resulting residual emission that is very similar in the shape and also for different epochs to the spectral 98 BW. I want to talk also about another event, GRB 060218, the third most nearby GRB ever known. It was also a very low luminous event, similar energy of 980425, but it was characterized by a prolonged X-ray emission. I must say that this was probably the first, if I remember correctly, the first GRB supernova observed by Swift. Swift, unlike Batsy and Deposax, still has, because it's still working, an X-ray telescope that can point immediately, the location of a GRB in the sky about 2 minutes after the GRB detection. So we had a complete mapping of the X-ray emission of this event, which was characterized by a prolonged, almost 3,000 or 10,000 seconds emission and soft emission in the X-rays, whose analysis led to the identification of an underlying black body component, thermal component. And this thermal component, after peaking in X-ray, evolved into the optical frequencies, because Swift also has on board an ultraviolet and optical telescope, which lasts for about 2 days. This second peak corresponds to the emission from the canonical supernova. This thermal component has been interpreted as the shock breakout supernova from the core collapse, emitted from the core collapse supernova. And actually, the shock breakout is the first electromagnetic emission observed immediately after the collapse of a massive star. And it originates from the rebound of material. You know that progenitor star of supernovae have this onion-like structure with the lighter elements on the most external layer and the most heavy element like iron in the central core. So since iron is the element with the highest binding energy, in order to ignite nuclear fusion to iron, we need to provide energy, unlike the other elements. And since at a certain point, we cannot provide such energy, it starts a neutronization process, leading to the fact that the radiation pressure of the iron core cannot sustain the gravitational pressure. So we have this collapse of all the external layer into the iron core. And then that lead also to the presence of a stalling situation that is solved by the emission of neutrino, because the neutrino, despite neutrino can very difficult to interact with matter. We have such a high density in the core of supernova that neutrino can actually really allow the expansion of the supernova. So this and neutrino also ignite a shock wave formation that propagates through the layer of the supernova, and when they reach the photosphere, they can emit. We can observe the first electromagnetic pulse, which is indeed the shock breakout from the supernova. However, in the case of GRB supernova, we also have the presence of, as mentioned before, a relativistic collimated component powered by the newly formed rotating black hole. And in the case of GRB, we have that as the jet propagates within the stellar layer, it creates a sort of lateral component. This effect can be observed also in our common life, in principle, but not at the densities and velocities that we observe in GRB supernova. This cocoon is mainly composed of it's composed by two components. One is the jet shocked material, and the other one is the stellar shocked by the cocoon itself. This jet can deposit a large amount of energy because it decelerates due to the interaction with the stellar layer. And the amount of energy that the jet can transfer to the cocoon is of the order of 10 to the 50, 10 to the 51 erg, which is comparable to the energy of the accompanying. It's about 1/10 the total energy of the accompanying supernova to the following supernova emission. And of course, since the jet comes from the most internal layer of the star, it can allow the mixing of heavy material to the most external layer of the star. And this is a simulation that probably you have already seen in a car talk of the propagation of the jet, the most dark component, and of the cocoon that when it is still inside the stellar layer, it is still, let's say, collimated, but once it reaches the photosphere of the supernova, it is free to expand laterally. And on top, we have the density, and the lower panel, the velocity component of the cocoon emission. So just to recap, in order to identify the cocoon emission in 1C broadline supernova, we need at least two ingredients. First, we have to identify an early thermal and cooling emission that cools from X-ray to UV and optical, and also later to radio emission. Then these components should be characterized by very high velocity due to the fact that the cocoon is highly energetic thanks to the transfer of energy from the jet. We should also observe a significant level of mixing, mainly iron peak element, or also nickel, cobalt, and titanium, and these elements that are around the iron in the periodic table. And we believe we have observed all these ingredients in another low luminous GRB and very close GRB 171205, which was associated with the supernova 2017 IUK, observed in a massive spiral galaxies, but still in the external region where we generally have star formation spiral galaxies. This is the swift but light curve of this GRB. As you can see, it's a very short spike and very faint. But the fact that this GRB was so faint reflected, as for the case of 033029, but in the opposite way, reflect on the afterglow emission. We had an X-ray emission that was very faint. And the fact that also that the afterglow was faint allowed us to observe a different behavior at optical wavelengths, different than typical afterglow behavior expected from optical GRB afterglow, in UV and optical bands. We have observed the presence of, we have detected a rapid color evolution. Let me see the time, a few minutes. In the first 2 days of the emission, this is the emission from the supernova. And we, thanks to the multi-wavelength photometric and spectroscopic campaign, we have been capable to build different spectral energy distribution in order to analyze the spectrum emitted by this additional component, and we found that it was best fitted by a thermal and cooling component, decaying from very high temperature to almost normal 10 to the 4, 5, 6, 10 to times 10 to the 3 Kelvin 2 days after the GRB, with a radius expanding from 10 to 12 up to 10 to 15 centimeter. Actually, we have identified this component using classical power law plus black body behavior, where the power law mimics, well, represents, not mimics, the afterglow, the standard GRB afterglow component, and just using only the power law component, we had easily identified an X-ray emission that was indeed modeled by a black body component. This was the first ingredient for the presence of a jet cocoon, but the most spectacular evidence came from optical spectra. We were able to observe, thanks to our prompt reaction, the spectra from these emission component using the Gran Tecan telescope in La Palma in Spain. And what we observed was the presence of a weird broad absorption feature that we have interpreted as due to ionized silicon and ionized calcium near-infrared triplet at very large velocity. This implies this satisfies the second ingredient for a jet cocoon emission, that we need a very high velocity component. And the last one came from a very detailed spectral synthesis model using the TARDIS code. TARDIS is a radiative transfer code, a Monte Carlo radiative transfer code that can can simulate the spectra of supernova 1A and core collapse supernova. This is another supernova that I have modeled and published in a paper of 2022, but it's a normal type 1C supernova. In any case, with TARDIS, you need some information related to the density distribution of the ejecta, the abundance composition of the ejecta itself and the bolometric luminosity. And then you can do a very iterative analysis trying to simulate all the spectra observed with the supernova. What we have found is that we can simulate the very early, the first 2 days spectra obtained from the cocoon. The spectra obtained at 0.06 was the very first spectrum obtained using VLT 1.5 hours after the GRB emission that did not show the presence of a, well, did not clearly show the presence of a cocoon, but there are some evidence that were never reported in papers. And in order to simulate the entire spectral sequences, we need to include not only an additional density at velocity larger than 50,000 kilometers per second. Take into account that when I talk about velocity, I'm talking about distance from the core collapse, because supernovae at these phases are in a, let's say, a Hubble flow expansion. So velocity is proportional to the distance. And so at a larger velocity, this means at larger distances, we, from the core, so in the most external layer, we needed to include relatively high abundance of iron peak elements. And we know that these elements are generally formed inside the most internal region of the supernova. This is the clear evidence that a jet has indeed transported these iron peak elements into the most external layer of the supernova emission. This is another plot showing the difference between the theoretical expected velocity from the CO138 model. The CO138 model is the model used for the simulation of 98BW. We have a very good agreement from the 3rd day after the GRB explosion, but for the first 2 days, we could not use the supernova component alone. We needed to implement our correction. And this is another plot showing the velocity distribution as inferred from absorption line in different GRB supernovae. This is really interesting because it shows that before 2017 IUK, we have only observed, we have only obtained spectra for GRB supernovae later on, at very late phases, which is 5 days after the GRB, which is not that late, but it's late for the detection of the cocoon. Indeed, the deviation from the standard power law decay of the velocity, which is due to the normal evolution of the supernova or the core collapse supernova, is also observed for 2017 IUK. But since we do not have data for other GRB supernovae at epochs before day 5, we could not say anything about the presence of the cocoon. This suggests that we actually really need a prompt reaction when we have a detection of a particularly nearby GRB supernova in order to find evidences for the cocoon. This is another image that shows the photometric light curve in V and R band as obtained from our multivariate campaign. I have also a multi-filter light curve, but in this plot, I'm showing here the differences between the two supernovae that I have shown before, 98BW, which is one of the brightest supernovae associated with GRB, and 26AJ. And you can see that the behavior, you can see that 2017 IUK is one of the faintest supernovae associated with the GRB, and also the behavior of 1C broad-line supernova is not that standard as we believe, as we can think about. In particular, photometric data shows, for the case of 2017 IUK, the excess at days before before day 4. This excess is indeed due to the cocoon emission. I would like to stop here because I have a meeting, just to briefly mention something related to the fact that the 1C broad-line supernovae, the majority of 1C broad-line supernovae do not have an observed gamma ray burst associated. Indeed, if we consider all the classes of core collapse supernovae, all 1C broadline supernovae represent only 1% of all core collapse supernovae. So I'm excluding type 1A supernovae, which are thermonuclear supernovae. And of this 1%, only the 10% of 1C broadline show almost real connection with a GRB event, with a collimated emission. This suggests that probably there is no, in the supernovae that are GRB less, so do not show a collimated GRB unassociated GRB, we could not have probably a relativistic jet emission. So probably not, we do not have a central engine operating. This is a bit weird because if you look at the spectra of GRB supernovae like 98BW and 26AJ with supernovae that are not associated with the GRB like 2002 AP and 97EF, they are very similar. So we do not have a GRB, but the spectral emission, the velocity, the composition is very similar. Also, information on the presence of a jet could also be inferred from late radio observation, given that the GRB afterglow, after peaking in the first day in the X-ray and then optical, it moves slowly to the radio emission. So late and deep observation in radio can, in principle, point out the presence of an off-axis afterglow emission. However, in 2006, Alisa Soderberg made a survey of a radio survey observing a lot of supernovae, but of these only 6 were broadline supernovae. She didn't find evidence of radio emission that could be associated with off-axis afterglow. And more recently, for the very bright and close 2014 AD, Marco Maronjo et al. Also did not find any radio emission, but they, after a detailed modeling made by them, did not exclude the presence of a large off-axis jet, large by of the order of 30 degrees. However, the velocity excess observed in the early spectral 1C broadline supernovae has been recently interpreted as a signature of a choke jet. What is a choke jet? So in principle, we can have a central engine, we can still have a central engine in the core of 1C broadline supernovae that for some reason does not feed enough the jet component that in order that this jet can break out from the progenitor star. But however, the jet would suffocate within the stellar layer, but still ignites a shock wave, a cocoon emission that slowly propagates inside the supernova layer. And when it reaches the photosphere, as in this simulation always by the group of Nakar et al., should break out and we should have evidence of the cocoon. So in this case, the jet is not fed by the central engine. So the jet is dead inside the star, but we have still the propagation of the cocoon inside the supernova progenitor. And once it reaches the photosphere, we should observe a jet cocoon breakout, which then can freely propagate because the density is very low. And for the Rankine-Guggenheim equation, you have an acceleration of the material and then a UV optical flash. So I don't want to go into more details because I have no time. Just want to show you, sorry, my conclusion that jets and of course rotation of the central engine can play a fundamental role in the core collapse of massive star. Indeed, probably for the case of 1C broadline supernovae, the neutrino heating mechanism is not enough to explain the entire phenomenology that we observe. For this reason, the characterization of jet cocoon emission could really help us to characterize much better the role of jet, not only in the formation of a GRB, but also in the not in the collapse of the supernova, but in the mixing and also in the emission observed by supernova 1C as well. And thank you very much for the attention.
Thank you very much, Luca, for your talk. So we are on time. We have a few minutes for questions or comments or remarks before the break.
May I ask something?
Sure.
Yes, of course.
Luca, I noticed you have two different regimes of deceleration when you show the plot of the velocity as a function of time. Is that because of the different densities or what? Do you have a model for that? When you show the velocity as a function of time, there are two regimes of deceleration. The first is sharp between 0 and 5 days, and then you have that one. Yes.
Because the first one is due to the cocoon. We actually are observing the absorption line from the cocoon emission that are rapidly decelerating. It has a very low density. The cocoon, it's very energetic, but it has a very low density. We have estimated density, I don't remember now what is the number, but from the TARDIS simulation, we have an estimate of the mass, should be 0.1 solar masses or less in the cocoon.
So this is because you have a change in the slope of the density profile. Is because of that?
We actually changed manually the density profile. We needed to increase the density at higher velocities. Look, the dashed line corresponds to CO138 model, which is the model used for the simulation of 98 BW. For 2017 IUK, we used a different behavior with a different power load decay, in particular at higher velocities. It's not probably very well shown here, but at velocity larger than 50,000, it varies the slope just a bit. So you can see the difference here in between from the dashed line. Density is much higher, but density of the cocoon in compare with the global density of the supernova. So you should integrate this region versus this region is much lower.
Yeah, very nice this plot. This is the first time I see it. Thank you.
Are there any other questions or comments? Okay, it seems not. So we thank the speaker again, and we will have a break, 15 minutes break. So it will be, we will reconvene again at 11:30 Central European Time. Thank you and see you in a bit. Bye. So welcome back to the second part of the morning session. And we will have the pleasure to invite to speak Professor Eli Waxman. So Professor Eli Waxman will speak about the new missions. So the floor is yours. Thanks.
Thank you, and I'm happy to talk to you about the Ultrasat mission. Let me share my screen. I hope you can all see the presentation okay. If not, you should tell me.
Yes, thanks. We can see it properly. Thank you.
Very good. So Ultrasat is a space telescope with a very wide field of view and high sensitivity in the UV band. And its main goal is to study transient astrophysical phenomena. We'll explain what our goals are shortly. The mission is led jointly by the Weizmann Institute of Science and by the Israeli Space Agency. You see here the key leaders of the project. And the funding is from the Israeli Space Agency, the Weizmann Institute, DESI, German partners, and NASA. I will say a few words about their contributions and about the contributions of our major industry partners later on in the presentation. So the goal of Ultrasat is, as I mentioned, to study transient astrophysical phenomena, things that appear for a short time on the sky and then disappear. A few examples are given in this table. Some of our key science goals are to study the collisions of mergers of stars like binary neutron stars or binary black hole neutron stars, to study supernova explosions, tidal disruption events of stars by supermassive black holes, and similar short timescale phenomena. We are interested, of course, as astrophysicists in understanding the physics of these sources, but most of them are related also to more fundamental open questions that we have regarding the universe. For example, the origin of the heavy elements beyond iron, which we believe is related to binary neutron star mergers, but we do not have a direct, clear confirmation of that. We don't understand how supermassive stars explode rather than collapse to black holes. We want to study the demographics of supermassive black holes and how do they affect the galactic environments in which they reside. So studying the transient astrophysical phenomena that we are interested in will also shed light on these fundamental open questions. What is unique about Ultrasat? There are many attempts to do wide field transient astrophysical surveys. So the key properties that make Ultrasat unique are that it has a very wide field of view of about 200 square degrees, and that it has a high sensitivity in the UV band, 230 to 290 nanometers, of about 1 photon, 110⁻³ photons per centimeter square per second. This large field of view and high sensitivity enables us to monitor a large volume of the universe. So if you look at the graph that appears here, you see that on the y-axis you see the volume that will be accessible for transient searches for different observatories, and on the x-axis you see the wavelengths at which these observatories operate. It's normalized such that Ultrasat is 10 in these units. So you see that Ultrasat is 300 times more sensitive than the most sensitive UV space telescope so far, GALEX, and it is about 100 times more sensitive than all current wide field survey observatories like the ZTF, for example. And it will be comparable in sensitivity to the Rubin or LSST observatory that is planned to begin operating sometime in 2024, which is a ground-based large telescope being constructed in Chile. In addition to the grasp or the large volume that Ultrasat will be able to monitor, being in space has some additional advantages. First, it would enable us to measure the near UV emission from these hot transient objects, which is not possible to do from the ground, of course. And it would enable us a continuous cadence from minutes to months observing these events, which is also impossible to do from the ground. In addition, we will have real-time alerts transmitted to the ground continuously. So we will be in a geostationary orbit. We'll have continuous communication. New transient events that we detect will be communicated to the world community within less than 15 minutes. So many other observatories, ground and space-based, could follow up our detections. And finally, again, being in space, we have continuous access to instantaneous access to more than 50% of the sky at any given time. So we will be able to follow up on transient alerts provided by other observatories like LIGO. We will be able to access any point in the sky in less than about 10 minutes. And again, transmit our observations and detections to the world community within less than 15 minutes. Two of our key science goals are gravitational wave sources and supernova explosions. Let me say just a few words about each of those. The detection of gravitational wave signals by gravitational wave detectors provide rather large angular uncertainty error boxes. So the exact direction of the event is not accurately determined by the gravitational wave detection. And so many observatories will attempt to identify, for example, the electromagnetic emission, which is expected to follow up on the mergers of neutron star binaries or neutron star black hole binaries. But this is going to be quite difficult due to the large error boxes that will be provided by LIGO and LIGO Virgo Cagra network. The advantage of Ultrasat is that it will cover, with its very wide field of view, the gravitational wave error box that is expected in 2025 within a single image of our telescope. This will enable us to rapidly slew to the alert position and cover the entire error box in a single exposure and identify and send notification of any new transient discovered to the entire community in a very short time. We will be able to localize the mergers to the host galaxies, and we will provide detailed UV light curves of the emission, which is crucial for determining the properties of the ejector. The second key science goal is the supernovae, as I mentioned. Ultrasat will provide high quality, so high cadence, high accuracy, detailed UV light curves for hundreds of supernova, starting quite shortly after the supernova explosions. What you see on the bottom histogram is the number of supernova that will be detected by Ultrasat per year in less than 1 day, shorter than 1 day after the explosion. The importance of detecting a very large number of supernovae is that we want to map the entire supernova progenitor and observable types to each other. So most of the detections would be of red supergiants, but we do want to detect breakouts from blue supergiants and Wolf-Rayet stars, and the large numbers that we will detect will enable us to do this. And in the inset, you see the number of ultrasat detections of supernova explosions within 1 hour of the explosion, and you can see that we'll have a significant number of those as well, while other large servers like ZTF and LSST will not be able to detect the supernova so early. Now, these early detections of the supernova will enable us to measure properties of both the progenitor star and of the explosion, like the radius of the exploding star, the explosion velocity, the surface composition. And will also enable us to determine the extinction towards the supernova, which is also crucial for interpreting the result. And it will also enable us to reveal the pre-explosion evolution of the mass loss of these stars through the detection of the UV emission that is expected from the interaction of the ejecta with the surrounding circumstellar medium. Let me just close the window here, there's some noise. Okay, just one comment about the detection of gravitational wave electromagnetic emission. So you all know that so far we have one detection of gravitational wave emission from a binary neutral star merger, followed by the detection of an electromagnetic signal. This is for the event that was detected in 2017. It was a very fortuitous event that happened very nearby, at about 40 megaparsecs from us. And what you see on the top right plot is the arrow region provided by the gravitational wave detectors, LIGO and Virgo. And on the bottom plot, you see a comparison of before and after images of the galaxy in which the electromagnetic counterpart was detected. You see the new source marked with those white bars appearing on the right-hand side figure. So this detection was achieved by telescopes with relatively narrow field of view, going over all the galaxies in the arrow box of the gravitational wave detection. And it took about half a day for the electromagnetic transient to be detected. Now, this exercise would not be possible for gravitational wave sources detected at larger distances. So with the upgrades of LIGO and Virgo, most of the events are going to lie at about 200 megaparsecs and beyond. And the number of galaxies in those arrow boxes is going to be very large. So again, ultrasat's very wide field of view would resolve this challenge by observing the entire arrow box in a single image. And second, the electromagnetic counterpart of this event was very dim in the infrared and radio, and it was very bright in the UV when it was detected. Probably was even brighter in the UV earlier than the detection. So ultrasat will be able to see such events to distances of 300 megaparsecs or more. Okay. So this event provides strong support for the ultrasat science case. I've briefly discussed two science goals, but with the dramatic increase in the volume of the universe that will be monitored of 100 to 300 compared to earlier surveys, ultrasat is going to have a major effect on the study of many transient astrophysical phenomena. I've discussed some part of the supernovae open questions. I've discussed the binary neutral star mergers, but you can see that there are many other science goals that will be addressed listed in this table. I will not go through the table, just mention that there are different science working groups in the Ultrasat collaboration, focusing on different open questions related to different transient astrophysical phenomena listed here in the table. I do want to mention one additional science goal, which is not a high energy astrophysics science goal, just to demonstrate the diversity of the science that Ultrasat will enable. And this is related to planet habitability. So you know that there are extensive searches for the detection of habitable planets, so-called, or Earth-like planets around close to solar-type stars. So most of the searches are around M dwarfs, which are both suitable for the detection of the planets, and in particular, the Earth-like planets at relevant distances. Now, these M dwarf stars are very active in the UV, and strong UV emission can severely limit habitability. On the other hand, it may enable prebiotic chemistry, which is maybe required for creating biological activity. And finally, the ionizing UV radiation can produce so-called biomarkers like ozone due to the dissociation of molecules, independent of the activity independent of a biological activity. So you may be misled to identify biological activity due to this UV flaring. Now, the UV activity of these M dwarfs is not well known, especially the frequency and amplitude of rare bright UV flares is very poorly constrained. And Ultrasat will monitor about 10 to the 6 stars of this type. It will be able to determine the new UV flaring frequency and luminosity of these objects, and it would enable us to characterize the dependence of this activity on different characteristics of the stars. And this will determine which stars are more likely to host habitable planets, and which planets are the best candidates for deep spectroscopic studies for biomarkers. A word about the mission profile, how Ultrasat will operate. So at the beginning of the mission, we'll do an all-sky survey, mapping the entire sky, producing a reference map, which will be much deeper than the galaxy map. Most of the time, we will be staring either in the north or south ecliptic poles, searching for transients in a direction which is suffering least from galactic extinction and from zodiacal background light. And occasionally, when we receive an alert about the transient, for example, from a gravitational wave detection, we will slew to the position of the gravitational wave or other transient source, and try to detect the associated UV counterparts. A few words about the implementation of the mission. In the center part of the slide, you can see the Ultrasat telescope. It has a very long baffle at the entrance of the fast F1 telescope. And this telescope is being constructed by an Israeli company, ELOP, which builds Israel's space observing telescopes. On the right-hand side, you see the focal plane array that would sit at the center of the telescope. This is the contribution of our DESI partners. The sensors, the UV sensors, which I will briefly describe shortly. These are the grayish tiles at the top of the focal plane array. They were produced already by an Israeli company, Tower. The telescope would be integrated to the bus to construct the full satellite by the Israeli Airspace Industry, IAI. And you can see this drawing of the full satellite on the left-hand side. The satellite would be launched by NASA to a geotransfer orbit that is not directly into a geo orbit, which requires us to carry a lot of fuel. So the satellite is mostly fuel in mass, and you see the dimensions and the masses on the right-hand side. And the launch is planned to Q2 or Q3 of 2025. A few words about the detectors. So the sensors are backside illuminated CMOS detectors, which have a unique dielectric coating to prevent charge accumulation, to increase the quantum efficiency in the UV, and also especially optimize anti-reflection coating. This brings us to quantum efficiency in the UV exceeding 60%, which is much higher than was possible until a few years ago. You see some of the characteristics of the camera on the table. It's about 100 megapixel camera, 10 micron pixels, and about 5 arc second per pixel on the detector plane. Very low dark current and read current, and high quantum efficiency, as I mentioned. The sensors have already been produced, and their UV characteristics have been measured at the DESI lab in Zeuthen. The lens material has already been produced. This is the first calcium fluoride outer lens of the telescope, and it is now being polished by Winlight to the specifications that we've designed. We are confident about meeting the technical requirements which are required in order to meet our scientific requirements. So what you see in this plot on the left-hand side, you see measurements of the quantum efficiency as a function of wavelength of the sensors. There are 3 different types of AR coating here, and we chose the T2 option. On the right-hand side, you see this is now a calculation, because the telescope has not yet been built, of the frequency-dependent point spread the function of the telescope. And you see the dark blue region, which is where we are going to operate, around 250 nanometers. You see that we obtain a PSF, which is less than 10 arc seconds. On the right-hand side of this plot, you see a measurement of our specially designed filter for suppressing out-of-band flux. So we achieve a better than 10 to the minus 4 out-of-band suppression. This is important in order to suppress the emission of red light, both from host galaxies of the events and also from the large number of M stars that will be in our field. So based on the measured quantum efficiency, the measured filter performance, and the calculated PSF distribution, we can estimate the limiting magnitude that we will reach. And this shows you the limiting magnitude as a function of the radial distance from the detector center. We will be going with the top curve here with the blue VRV filter, and this allows us to meet our scientific requirement goal of about 10 to the minus 3 photons per square centimeter second sensitivity, which corresponds to 22.4 AB magnitude in the UV band. A few words about the status and timeline of the project. We have completed the CDR in April of this year. and the program is on track according to the schedule table that you see on the right-hand side. The industry teams are fully composed. They are working full steam ahead. We believe that we've identified and are managing all the major risks to the mission. So one of the major risks was achieving the high quantum efficiency of the sensors and meeting the stringent PSF requirements across the very wide field of view. But these risks have already been retired, so we have demonstrated that we meet these requirements. The remaining major risks are the timeline, which is very challenging for a space mission, the complex interfaces between the different components and different industries, and the contamination issue. Organic molecules that accumulate on the optical surfaces can lead to significant degradation of the UV transmission, which implies that first in designing the satellite and the telescope, specific materials that have significant outgassing of such organic gases are avoided. The entire construction should be carried out in very high quality clean rooms to avoid any contaminations. This is a significant challenge at all stages of the construction and the assembly of the telescope. And we also have designed an outgassing heating of the telescope in space in order to release contamination that would be accumulated while in orbit. The camera or the focal plane array is expected to be delivered at the end of 2023. Then the telescope is expected to be delivered by the end of 2024, by the middle of 2024, sorry. And the satellite is going to be ready for launch at the beginning of 2025. As I mentioned, the launch is planned for Q2 or 3, 2025. The entire mission cost, including launch and operations, is about $110 million, which is a fairly low cost for such a space mission. Few words about the Science Operation Center. So the Science Operation Center is being constructed at the Weizmann Institute, and it will support all the scientific aspects of the operation of the satellite. We will have a 5 megabit per second downlink from the satellite to an antenna at IAI, the Israeli Aerospace Industries. This will enable us to download all the data from the satellite to the ground in real time. The data will be transmitted to the Science Operations Center here at Weizmann in real time. This is where the images will be analyzed, transients will be detected. This is where alerts will be disseminated to the world community from. This is where the data will be stored and archived. And this is where the observation plan of the satellite will be carried out. A few words about the scientific collaboration. The Ultrasat team includes 13 science working groups. Working group members receive immediate access to all the data products. In general, we will have annual data releases, so the data will be proprietary for about 1 year for the working group members, except of course for the transient alerts, which will be distributed to everyone in real time. The science working groups are open to all the Israeli astronomers, and most of them are already part of this mission. Our DAISY partners received 3 PIs in the working groups in return to the contribution of the focal plane array. And NASA would receive some 8 US PI working group members in return to their contribution to the mission by providing the launch. NASA has already identified and appointed a project scientist, James Rhodes, and he will be issuing a call for proposals to the US community in the coming months. Finally, we are in advanced negotiations with the Rubin Observatory. We will have a cooperation with Rubin. Rubin will receive additional USPI working group members, and in return, they will receive also some memberships in the Ultrasat working groups and access to some of the Ultrasat data. To summarize, Ultrasat will revolutionize our ability to study transient hot events in the universe. It will have a discovery volume which is 300 times larger than GALEX and about 100 times larger than any current observatory. It will enable us to identify and measure the emission from transient events continuously with a cadence of minutes to months at a sensitivity of 22.4 AB magnitudes in the UV. And it will provide real-time alerts with very short delays of less than 15 minutes to the entire world community. These unique properties will enable us to bring an impact to a broad range of astrophysics topics, from gravitational wave sources and supernova that we've discussed, to the UV stellar activity, AGN activity, tidal disruption events, and many other topics. The mission is not cheap. $100 million is not cheap, but it is what we call affordable. It is a low cost for a groundbreaking space mission that proves that groundbreaking science space projects can be constructed at an affordable cost, which is much lower than the typical cost missions of NASA and ESA. And this enables other players to join this field, and not only a very large consortia. Finally, we believe that the scientific results of Ultrasat will have a high profile, and it will therefore very positively affect education in Israel. It would contribute to attracting young students to science and technology. And we are working with the Davidson Institute and the Schwartz-Rassmann Institute here at Weizmann on an extensive outreach and education program related to the Ultrasat mission. And if you are interested in learning more about Ultrasat, we of course have a webpage that you see the address of here at the bottom, and you are welcome to read the information there and send me questions if you want, and contribute if you think it's relevant. Thank you.
Thank you very much to Professor Waxman. Now it's time for asking questions or comments or remarks. Is there any question or comment? So maybe I have a quick question. Maybe I missed, but what it is like the foreseen like length of the mission, and what it is the sort of expecting, in the sense that usually mission they are targeted for a given amount of time, but then we know already that they will last longer. So if you could point out a bit on that.
So the mission is planned in terms of reliability requirements for 3.5 years. Satellites, especially the Israeli satellites, typically live much longer than the designated reliability time. So we carry fuel, we need some fuel for maintaining the orbit at the geostationary position. So we will carry fuel that will enable us to extend the mission lifetime to 6 years. So the current mission lifetime plan is for 6 years.
Okay. Okay. Thank you very much.
Maria Giovanna,
yes.
I have a question.
Yes, of course.
Hello, Eli. Thanks for your talk. I have a quick question. I didn't understand if the satellite will operate, can operate in target opportunity modality, or the satellite will observe a certain area of the sky, and there is it will be not too much flexible in moving around when something interesting will show up in the sky. Thanks.
Okay, so most of the time we will be staring at a fixed position, which, as I mentioned, is either the north ecliptic or south ecliptic poles. So this will maximize our sensitivity, because these are the directions where extinction is minimal and zodiac light background is minimal. Now, we are very flexible with the TOOs. We can access in less than 10 minutes any point in the sky. So once we receive a TOO and we decide that it's an interesting opportunity, we will slew to that position and observe it. We can observe at any position on the sky for more than 3 hours. So including positions where we don't have sun on the satellite, which is limiting power, we will still be able to monitor, to observe for at least 3 hours, and we have continuous communication in any position. Now, there is essentially no limitation to the number of these TOOs, except for what we call hard TOOs. Those TOOs for which we don't have sun, which is about 1/5 of the TOOs, they would their number is limited because they are discharging the battery. So we have some limitation on 20% of the TOOs, but essentially we are unlimited in the TOO capability.
Thank you so much. Thank you. Very interesting.
Thank you very much. And did you already establish the policy for sharing the data?
So, yes, so this is a sort of a joint policy of our space agency, NASA, and DESI, who are the major partners to this mission. So all the data would be released annually with approximately 12 months delay from our onset of operations. Working group members would receive immediate access. All the members of the working groups will have immediate access to all the data. Transient alerts would, of course, be instantaneous to everyone, because we think it's best that everyone would try to detect and follow the events that we...
Vuol dire, Raim, se può venire, o anch'io...
There was an interference. But for example, so if people are interested in collaborate, then they will have access to, immediate event. In case some event is of interest of like people from external group, it is possible to collaborate. Yes, as you mentioned, that people that are interested can contact you and
right.
join
so
one of the working groups.
Right. So we have 13 working groups, and working group leaders to each of these groups. So if someone is interested in in a particular object and he wants to collaborate with probably would be no problem. So we would be able to communicate to the science group leader and say that he's interested in something, and the group will decide if his contribution is valuable to this study, and he will be able to be accepted. For something which is more long term, then if someone wants to join now these working groups, if he brings some important resources, okay, so we would like to have follow-up spectroscopy, let's say, of objects. So if someone says, okay, I have these resources that I can bring into the collaboration for follow-up spectroscopy, then the relevant working group would be able to consider this and say, oh, yes, this is an important contribution. We can join forces and we can collaborate, give some data rights to this, to whoever brings this additional.
Okay, thank you.
If you're interested in this, yeah, I should mention the project scientist is Yossi Schwarzwald here at Weizmann. He is coordinating all these activities. And so if you are interested, you can write me, you can write Yossi, and we will disseminate it to the working group leads. We have a science board composed of the different funding partners. So these decisions would need to be authorized by the science board, but this is the path that would be taken.
Okay, thank you very much. That it has been very interesting. Are there any other questions or comments? Okay, if not, we thank Professor Waxman again, and we move to the next speaker of the session before the lunch break. So the next speaker is Yerlan Aymuratov. He will speak about several GRBs at 130427A, 190829A, 190829A, and 190114C, for which we have already heard the previous talk. Thanks.
Okay, do you hear me? Hello?
Yes, we can hear you well.
Let me share my screen. So, okay, I need some. Privacy issues. Let me reconnect because I need to give an access to share my screen. Okay.
Okay, yes.
Okay, hello again. Let me.
Yes, you can try sharing the screen.
Here it is. Do you see my screen and is it moving?
Yes, but it is not in the full mode. If you can show in the full mode, that it would be great.
This one?
Not in the full mode yet.
Okay.
Well, we can still see. If you have difficulties, maybe we can start this way. Anyway, it's visible.
Oh, okay, let me see. So, hello again. Today I will present some preliminary and published partially results of our group. And the topic is connected to the gamma ray bursts associated with the supernova. The whole day is dedicated to this as well. And I will give a flavor of what was told already from the sense of particular cases of these three GRBs presented. And this work is done in collaboration of people from Pescara. So you hear me, I guess, yes? Hello?
Yes, we can hear you. Yes,
okay.
We can hear you.
Okay, so As you may know, so gamma ray bursts are observed on the entire electromagnetic spectrum. And as well, there is non-electromagnetic messengers, which opened an era of multi-messenger astronomy. So we observe the signal from gamma ray bursts in the whole variety. And today I will cover a little bit of background, because since it's a school, we should cover a bit of background as well. Then I will concentrate on our methods, which is actually well known and widely used. And we will show and discuss some bit of results, which was already, presented from the sense of the prompt emission and from the sense of general connection. I will just make a point.
Are you changing the slide? Because we still see the intro slide.
You still see my intro?
Yes, I realized that maybe you're okay. Now we see the second one. Yes.
Okay, so here is the second slide. So it's like a whole electromagnetic spectrum, and I say that there will be a little bit of background. Okay, little bit of background and then methods used, and results to discuss. Okay, so the first observational fact, it's a crash course to GRBs. You should know that the GRBs observed on the entire sky. So they are isotropically distributed on the sky, and it means that they're extragalactic. It was proven in 1993, it was already said. That means that they have a high Z, high redshift, and the distances are cosmological. And it is clearly shown on this picture of 10 years of Fermi GBM data, which covered long and short GRBs, I will say in a minute, which is distributed on the entire sky, as you see. So to the moment of 10 years of Fermi observation, there were more than 2,000 GRBs observed, and the whole, like for more than 50 years, we observed more than 8,000 objects, gamma ray burst events, and the distances to them vary very widely, and there are extreme cases of GRBs which appear just after the end of the reionization era on distant universe, and there are many more cases of bursts happening nearby in the relatively nearby universe. So there are prominent cases, and from the point of data analysis, and I will cover mostly from the point of data analysis, it seems very interesting that how is it covered. But it's already said there is like a strong bias towards we see. It's like Almquist bias, because faint objects, if they exist, they are not seen because of the distance and the limitations the light can propagate through to the large distances. Okay, the second observational fact, if you want to work with GRBs, that they are temporal. They have a temporal bimodality. So it is well established long and short duration GRBs, and nowadays. And before it was a hint to the progenitors, and nowadays it is more or less well established that there is strong evidence that they have different progenitor system. That's why they last longer or shorter duration. And a little of statistics from the point of data, there is like short GRBs with the harder spectrum, and they are less in number than the long GRBs, which are softer in spectrum. And it was confirmed by many missions. Every mission dedicated to GRB studied, especially this distribution, still working. And there is like intermediate cases as well, very interesting, showing prominent features of both families, both groups. But nevertheless, the distinct peaks we see, and it is consistent with the early observations by BATSI, by SWIFT, by Fermi, and other missions as well. And the third observational fact, you need to know that we observe as well GRB's light curve, the images we do, and we observe as well the spectrum. And the point which was also shown before, and that is the uniqueness of the light curve. So light curve are unique in each case. Like here, you can see the early pictures of Bardsey. So you can see the prominent peaks, several peaks, single peaks, the so-called Fred pulse, and multi-peak structure. And they are unique. There are the simple calculated Fred-like pulse, which is, interpreted as the outflow just propagating into the medium. But there are many more cases which need to be studied, and it is of course related to the environment around, and the geometry, and so on and so forth of the
There is a problem with the connection. I don't know if it is only from my side.
We cannot hear also.
Okay, so I hope that this will be resolved soon. I still cannot hear anything. So Yerlan, can you hear us? I think he cannot hear, so I'll just write something in the chat. Maybe he can hear in the chat. Yerlan, can you try to share the screen again, because we couldn't hear you for the last minute or so. Okay. It seems there are still problems.
Okay, you see me now again?
Yes, yes. Okay.
Okay.
Yeah, so if you can share again and repeat the last slide you were talking about.
Yes.
Thank you.
I stopped here or here? Here.
On this one. On this
Okay.
one.
Okay.
Yes.
Despite the variety of the light curves, there is a uniqueness. There is a commonness of the spectrum, and mostly the spectrum, the gamma ray part. Now I'm talking the gamma ray part of the signal mostly consists of this kind of picked structure. So there is like a distribution of the photons on the near spectrum across the energy is imaged so that there is a prominent peak, and where the most of the photons coming in gamma rays, and there is like a high energy tail as well, and there is like a more populated, less energy PeV to MEV photons appearing. Sometimes there is a signatures of the black body. Here you see is clear contribution or to the classical band function, specifically called band function because of the name of the person who did this work first. And more or less the spectrum of the GRB looks like this, with a small variety. There could be as well the power law spectrum, which simply goes with some index of minus towards the high energies, but more or less they're the same. So there is like a cutoff energy here, and sometimes you can see cutoff on the high end of the energy. And to the moment, the statistics of the Fermi GBM catalog of the 10 years says that they are well fit with the band function or Comptonized, so it's a cutoff power law function. Okay. Yes. Since there was a whole variety of the spectrum, we can see the GRB in, and we see the commonness of the spectrum in the gamma ray. Of course, we search for other similarities. So we see we search for the similarities in the afterglow, and there is like a prominent work done by Professor Bin Zhang of yesterday and the NAUSEC with collaborators in 2006, where they found a typical structure of the afterglow, or the X-ray afterglow, which more or less consists of several episodes. Like here, it's shown like 4 or 5 episodes with the sometimes it appears here as like a flares of X-rays, which is also interpreted to be related to some physics around the GRB. But it seems that the GRB afterglow also follows some similar structure. Since it was done for gamma ray and X-ray, we searched further, people searched further for the similarity in the optical afterglow. And it seems to exist as well with, of course, exceptions, as many as they can be. And it is done in 2012. It was, collected and presented in a way that it has also some prominent features. As well, it follows some structure, which is as a template shown for every optical afterglow, which we can follow on the ground or in the space. So this is about the image and the spectrum. Another stuff, when you have data and you need to point it to the theory, there is an intermediate bridge, which is called the phenomenology. And the phenomenology works in such a way that you try to find a correlation, then interpret this correlation in terms of the theory. And the one prominent bridge on this phenomenology is the so-called ISO bridge, which was also presented by Professor Amati the days before. And it says that in the spectrum, you have this dependence of the peak energy of the spectrum you see before in gamma rays, and the total energy radiated in assumption of isotropicity of the gamma ray burst. Okay, it also works for some case for the beaming, but in general case it's isotropic radiation. And for the first case, it was presented in 2002 with only 12 sources. Time passes, many missions are launched, and statistics came that this correlation still holds. And within 3 sigma, I guess here, all the long GRBs, it should be remarked, it's a long GRBs with redshift measured, which allows us to calculate the isotropic energy and the peak energy at the rest frame of the source. Can show this correlation. It has some background meaning, or has not. It is well discussed, widely discussed in the literature, but it is a phenomenology that brings us as through the bridge to the theory we can calculate and evaluate through. So I told that that correlation was built for exclusively long GRBs, but since we always search for similarity as human beings, we search the similarity and ask the question: is it exist for the short GRBs? It needed a long time since short GRBs are harder to catch, and especially harder to catch in the optical afterglow to measure the redshift. But it seems to exist as well. So in 10 years after Amati correlation, there came like Zhang correlation, which consisted only dozens of short GRBs, well measured with redshift. And it seems to follow more or less the same slope. Here's the long GRBs below, more or less the same slope. And as time passes, again, the missions launched and statistics came into operation also. We have here the 30 GRBs to the date of 2018. It already appeared the famous 17087, and even more prominent 090510, and they stay within this 3 sigma limit of this correlation as well. So it holds. And now I came to the phenomenology also of the GRB associated with the supernova. So whatever was covered before, it was a short introduction to start to work with GRB. And now we came to the phenomenology of the GRB associated with the supernova, okay? And it was discovered in 1998 during the first catch of the X-rays and optical was available. And to the present, there exist two methods to detect a supernova associated to the GRB. Okay, the first method is photometric. It's imaging of the source on the sky, and it shows you how the signal fades according to the time, with time, and it is relatively easier to obtain. And unfortunately, fortunately, it is wide. There is a wide ground follow-up of this on this campaign. We can do with relatively small telescopes, even small telescopes. We can do a follow-up and see how the source is fading with time. And there is like a prominent bump. You can see, for example, here you can see optical in blue and optical in green and X-ray in blue, just to compare the signals and how it evolves with time. So the decay index is with a negative sign, and with time it goes, below the threshold, and we anymore cannot see it. The association of the supernova with GRB is given with this characteristic bump in the fading light curve of the GRB. So to be precise, here is the slope, or for example, this minus 0.91 of the GRB afterglow. Okay, and here we see the bump, and it is believed, and it is said that it is a contribution from the emerging supernova of going to the peak of its light curve. So there is like a contribution, and it enhances the overall signal. Here's the magnitude, but it could be as well in the luminosity. So we see the source rebrightening again for a short time and goes down, further. And the prominent is that this rebrightening happens on 7th to 15th days. So it's a clear signature, which was well studied before of the, it's called like a nickel decay, and produces the light, which is, rebrightening the source. And there are many cases of, optical follow-up, and you can see that the bump, this prominent bump, it is called bump, can be seen in the fading optical afterglow. So people study them, they collect them, and try to find other similarities and make some correlation, and then find some theoretical interpretation of it. Another and more robust is the spectroscopic identification of the supernovae in the spectrum of the GRB. So, and it tracks as the spectroscopic analysis does, is that tracks the absorption and emission lines of the spectrum associated to some futures of unknown elements, and that's how, for example, some elements presented in the outflow of the ejecta is tracked and identified. And it is relatively harder to obtain, because for the spectrum you need to collect more light, and since you disintegrated into the spectrum, you need more light, and this is a work for largest telescopes on the ground. And they are very busy, and the large telescopes are very busy, and not always you have the spectroscopic follow-up on this case. Many more conditions are related, like moon weather and so on and so forth. The typical spectrum, and this is canonical spectrum of the supernova associated with the GRB, looks like this, and it is shown here how it is evolved with time, and there's like a phases to the peak of the light curve when it goes to the peak, and how it is fading with time. And you can see as time passes, some futures as absorption and emission lines occurs, and we can identify it, easily. And there was a collection of the spectrum, and it is as well presented in the review by Kano in 2017. And you can see that there is like, you can see some commonality, but mostly they are, they are different. You can group them, of course, and it is said by Professor Della Valle that these supernovae are type 1, type C, and broadline supernovae, and it is identified through the lack of helium and hydrogen and other prominent lines in the spectrum which can be tracked. Okay, and if you put them on the, if you study these GRBs associated with the supernova, so we talk about the GRBs, GRB part, gamma ray part, and put on the set above EPK isocorrelation, you can see that they are grouped in several. So then you subdivide it in several categories by supernovae. You can see that there is, like, they are grouping in somehow, but then some inconsistencies occur. I will discuss it below. Okay, so why do we need to study the phenomenology? Is it interesting to study, and how we can improve it? So these are the questions we ask ourselves. They are not so many, and it was shown, the statistics, they are very less. It is around 1% of the whole GRB we catch to the moment, and but it could be a true signature what we can have on site, but it could be not seen or present or not present. So since it's a prominent and it's a special case in phenomenology, we need to study it well in order to have some, have some points to rely on, because the more theory we have, the more complicated it goes. But from the point of data, as you have data and you have two separate phenomena, the GRB it is discovered far later than the supernova exists in the history of human being. And it could be interesting to connect this two phenomena and study it in accordance to what we have and what we see. Okay, so now we go to the methods, and the methods are, first of all, we need to separate that GRB supernova which from the data you have. And as was said, so this statistics is built up to the end of 2020. There are 60 GRB supernova identified, both with photometric and spectroscopic methods. Okay, and there are good data, bad data, and we sort them further. We do subsample of this, but there are 60 to the moment of 2020, and Professor Dainotti said there are 69 to the moment, so we need to refine it, and maybe we can
yes,
cross-check this data to be our analysis more complete. And 60 is a quite round and beautiful number, and interestingly, the 30 of them occurred before Fermi, and 30 occurred within the Fermi era. And I cover here the Fermi and emphasize this because, as I said, GRB covered the whole electromagnetic range, and Fermi allows us to cover the GeV, high energy part of this spectrum. And it is interesting how can single event produce such a variety. It is intriguing and somehow puzzling us. And to study, like, in a fine structure, Fermi data from gamma ray part is very important. So what we do, we just cross-correlate information from all the sources, all the information sources we can find, and as well many big tables done by Professor Greiner, Kolpin, with other collaboration and missions. There's IceCube data table we use. Of course, the satellites and the GCNs and the SIMBAT database. And those of articles where people analyzed and find for example, the light curve, the spectrum, the lines, and the photospheric velocity, and so forth and so on. So we need to cross-correlate this information to have wealth of the data, which is covering, good, which has the good coverage. So, and that 60 objects we have, they all, of course, they have the redshift measured, and you can say that, and it is known that they are quite local. So since we have a limit for the supernova observation, then we have a limit for the redshift as well. Nevertheless, the GRBs are more distant, so it is again puzzling us. So are they associated supernova far away? This is another question to ask, and it is quite impossible to answer now without the missions and the instruments capable to catch this farther. And there are other limitations for the supernova as well. So I told this is quite interesting. And what is interesting in this sample? Again, I come to this graph by Kano, and you can see that they are grouped. So the GRBs, there's like a low luminosity GRBs, intermediate and ultra long GRBs. This is a future of GRB itself, and it says nothing about the supernova. So just neglecting the point that we have the supernova, what we can say, are they grouping different? Maybe they have some true signatures we can study further in a fine structure. It seems that there are some outliers, some prominent grouping, but not as well. There is also a spread in energy, which further moved us to idea to study it in more detail. So, and we do the standard procedures, and we take the optical data and convert it to the with known procedures to the bolometric we do the bolometric correction, and we do this standardizable and move it to the maximum peak of the phase, and then we do kind of a stretch also. And it is done as well in the previous works. For example, the Melander, it was also mentioned today, and studied in detail how this curve evolves with, for example, this modeling, which allow us to calculate as well the mass of the nickel, the mass of the ejecta, and the kinetic energy of the supernova, and somehow related to the observed GRBs, the gamma ray properties. So now I'm coming to the results, and it will take more or less 3 minutes. So I think I'm in time now. Within the analysis we done, and this is the peak time and the rest frame of the supernova, which was shown here. For example, we just put it in a peak, but they are spread; they occur in different times. Versus the isotropic energy in gamma rays of the GRB, says us, despite the peaking time is more or less similar with average value of 10 to 6 seconds, and it is actually accepted and known, we have a huge spread in energy, huge spread. So the question which rises, like how this energy deposit in a single event can create this standard supernova, not a standard supernova, but of core collapse supernova of some type. And another point is the luminosity. You know that the luminosity of the supernova is much less than the luminosity, for example, of the GRB itself. And here the average value of 10 to the 43 around. There is like a true clustering here around this average value. But again, there is a huge isotropic energy. And we are saying from the point of the deposit of energy of initial, for example, energy, burst energy, which we can see and calculate backwards. As Professor Della Valle said, you can do the back calculation and do also beaming, but it's a factor of 3, not more. So I'm here the factor of 7, order of 7 of difference in energies. these are big questions. And we also did like this redshift, how the redshift dependent on the peak time, and you cannot see also, you can see also the widespread in the redshift, and not more than one, of course, but still, which all of this and stood within our interpretation of binary-driven hypernovae of the binary system. So single event could consist of two separate phenomena, which can interplay with each other. But as was said, the supernova launching this process, so the burst of and the core collapse of carbon-oxygen core can launch this process and play with the neutron star around to accrete the matter and produce. And here there comes the difference in the conceptual view that the BDHN1, and of course I update you, the BDHN1, the case where the accretion comes and passes the limit and the neutron star collapses to the black hole. Here the energy is not enough to collapse to a black hole and creates a more massive neutron star. And here nothing happened, and there's like a fallback accretion of the new neutron star, which was created during the supernova, and there's like a material falling back to it due to the gravitational attraction, of course. And this stays in a good agreement with what we see here. So it's a widespread can be due to the geometry and scenario of a unique event of the burst itself, but consisting of a binary system. So the binary system opens you a door where you can play with different scenario. And now I came to the last 3-4 slides I have, and it was already shown. So I have not much to say. Just from the point of the supernova, we can see here in blue at 10 to 6 seconds, we can see the peak, although it's not seen like prominent, but you can see in red lines and the yellow line in the solid, you can see the fading of the X-ray, and it is due to the synchrotron and synchrotron radiation. And here you can see, and it is well seen in comparison. So you can see that the synchrotron, for example, the black dots and the corresponding decay line of the X-ray, it stayed within 1.1 to 1.4 index of decay with negative sign, and it is not like so correlated to the optical, you can see. So it is pointing us to, at least for us, it is pointing that these two phenomena are more or less separated. And as Professor Della Valle illustrated, the railways, so they launched together, but they evolved them separately, maybe interplaying a bit on the way, but mostly they are, triggering each other, and then go separate. And you can see that these signatures as, there isn't like, they couldn't be below the peak, they can be even above the peak, like here. And the way it is, the peaking time is standardized and happening on the more or less the same time, and the X-ray and the farther optical of the gamma ray burst evolves separately, hints us, at least to us, that this binary system is well constructed and plays this game with, with itself as it was, not related to the supernova. I mean the GRB. Okay, and based on these observations and the data analysis, several times we did our group did a prediction of the supernovae, and this is the famous supernova of 2013. There's like a supernova of 2018 as well, the prominent of the TeV. the group did. And still it holds our view that the key and answer to this is the binary. And the supernova, which we can see in all of these cases, are launching the process, and the explosion of the supernova, of course, launches the process, and it is then practically nothing to do with the GRB and ejecting the material. So here is the scheme how it is going in the 3D simulation, I guess. And there's like a different scenario you can see, and how it goes with the GRB itself, with the new neutron star, and the optical supernova, which occurs later on. Okay, so just to summarize, we did this observation. We collected the sample, then it's a subsample of data with a good coverage of data. Then did data evaluation for the volumetric correction, and modeled this to extract the ejector mass, the nickel mass, which is more or less consistent with the literature. Then, according to this correlation, or let's say a lack of correlation with the gamma ray part, we match it to our interpretation of the binary during hypernova. We progress like more than 20 years. So that's it to the moment. Thank you. If you have a question.
Thank you very much for Yerlan to give this nice talk. Are there any questions or comments? Okay, so I wanted to maybe remark again how it is important, this graph that you were showing about this luminosity of the supernova versus ISO, because basically when we try to do the search for correlation, we were sort of maybe expecting some connection, but because of what you were explaining, and also what Massimo was saying, we couldn't see any clear correlation. So I think this is remarkable.
Yes, and it was indirectly said before in some literature, but
yes,
not always collected.
Not explicitly.
Not collected in a big sample. And
yes.
Our aim was to show this. And the spread of energy is obvious. So, and since the discovery of 170817, it's from 46, 10 to the 46, and up to the 10 to the 54. So it's like eight orders of magnitude in energy, isotropic energy actually. And if you introduce beaming, it increases and deviates a little bit. But for the luminosity and for the supernova, you as well know that it's less luminous. Okay, and there is like a miscorrelation, so lack of correlation here. Yes. Our aim was mainly from the point of data. It's clear here from this graph, and our point was to show this explicitly with as much as we can collect from the data of the sample.
Maria, explain again.
Yes.
Can you repeat your question?
So mine was more a comment, because when I was working on the search of the correlations, this correlation did not appear, and it was not clear to me, the reason why. But now, after the talk of Massimo and the talk of Yerlan, it's much more clear why we wouldn't then see this correlation. So I think this is remarkable, because as Yerlan said, it was maybe implicitly said in the literature, but nobody has explicitly analyzed this so much in detail and with so many GRBs.
Yes,
so I think,
but I think there is a key point. A key point is that you cannot explain the difference between different BDHN GRB in terms of the luminosity of the supernova. Therefore, this is a fundamental point, and this is the reason why you need the BDHN model. You have to look into the physics of the BDHN model. And it's clear in the BDHN model that the trigger must be the supernova is fundamental. And it's always similar. But the binarity of the system, the presence of a black hole, the presence of a companion a neutron star in the binary, the supernova are part of the game. And the fantastic point that BDHN allows you to understand is how, starting from a standard supernova, you can differentiate between all these systems. This is the topic that we'll discuss even tomorrow and the day after. I mean, but this is the crucial point. The crucial point is to explain how, from a standard supernova, you can differentiate among 3 different classes. And for this, you cannot proceed with a single origin of the GRB with jet. You need necessarily the black hole, the new neutron star, and the binarity. And these are the next topic that you will hear also tomorrow in the exceptional result of Wang Yu. And of course, Jorge will give the overall picture. And we like very much to collaborate with you on this because it's very much related to your work as well.
Yes, definitely. Okay, so thank you, Professor Ruffini, for your comment and extra explanation. So I think now it's time for lunch break, but I've heard that there is still another change in the program. Or am I incorrect? Because I think
Liang will speak tomorrow, and Laura Becerra will speak later, I presume. Yes.
Okay, so but Liang will not speak today, yes?
No, we'll speak tomorrow.
Tomorrow, okay, so the schedule will have like a larger time or we will have Laura speaking earlier?
Having a good lunch or dinner in your case.
No, the talk just exchanged between Liang and Luca today.
Yes, Luca gave this morning.
So they
Yes,
exchanged.
okay.
It's okay. We have a longer break. See you later.
Okay, so then what time we need to reconvene? I'm sorry, I got a bit confused by this
15:45,
change.
I presume. 15:45.
15:45. Okay, thank you very much. See you later. Bye.
Thank you.